life can throw you some curves. And it's not just the things that you see coming, but sometimes it's the things that you didn't see coming that hit you out of nowhere, that set you back in such a way that it seems like you can't get over. And you've reached your limit and your bandwidth is full. You already said, I can't take another thing. And then out of nowhere, here comes something you didn't see coming and you're in it.
And in your homes, somewhere in your heart, these words are echoing. Am I going to make it?
When you get into a tight spot and everything goes against you until it seems that you cannot hold on for a minute longer, never give up then, for that is just the place and time that the tide will turn. There are times when your energy feels so depleted that you want to give up, that it looks just totally impossible. And I can tell you from my own personal experience, don't give up then. That's when you've got to fall forward, when life is kicking dirt in your face. Don't give up then. That's when most people turn back.
As long as you're alive, there is hope.
You're still alive. You're still here.
It's never too late, and it's never too dark, and we can always turn things around.
There's going to be bad days, there's going to be dark days, but you got to embrace it, because that pain is what makes you stronger.
Pain is the high cost of growth. If you want to grow up, you want to be mature, there is no way to do it without pain. You can't grow up on easy street. And the very thing that discourages you is the very thing that develops you.
No one's coming to save you. No one's coming to save you. The only person that's going to make a drastic change in your life, whether that's physically, mentally, emotionally, spiritually, the only person that is going to dig you out of your hole is who? You. You have to do it for you.
You've got to become courageous to stand up within yourself, to face it and step forward.
We all get a taste of that victim mentality, the why me? You can become the victim of the situation or the victor of the situation. You need to be the master of your emotions, not let them affect you. You're the dictator. You're the captain of your boat, whether you let things affect you in a negative way or a positive way. I don't lose. I only win or learn. In life, there's only winning or learning. All your problems become gifts once you learn from them.
And some of you have allowed adversity to make you stop. And I'm telling you right now, don't give up. I'm telling you right now, don't give in. Get through it. Execute, execute, execute. In the midst of adversity, execute. You're gonna work through this. You're gonna get up, you're gonna get dressed, you're gonna get out, and you're gonna do what you've been called to do. You're gonna be what you called to be, and you're gonna prove to everybody that tried to break you, everybody that tried to kill your dream, you're gonna prove all of them wrong. And if you can work through your pain, I'm guaranteeing you, on the other side is a reward. Pain is not permanent. Pain is temporary.
If that video resonated with you, please visit me during office hours to chat. More than happy to talk with you about this class and just life in general at the University of Michigan. And especially for those of you who are facing challenges, please reach out. If not to me, reach out to CAPS, which is a unit on campus available to meet with and help all students who in any way are struggling. And certainly in the year 2021, I'm hoping that we move beyond stigmatizing those who struggle. I lived with it for a long time, and I really hope that each of you who recognize mental health challenges can address those as young as possible to live really great, fruitful lives. So I want to return to a slide that you've seen previously. And I can't remember if I asked an exam question on this, but it's possible I could on the second exam. I just want to make sure everybody has a good appreciation for what these data tell us. You know, if you take the y-axis without even knowing what the units are here, and you look at each of the lines labeled consumption and extraction, right? And we follow my cursor, right? If we go back to North America up here top right, we can see that we extract iron and steel, okay? Or we extract iron for the purpose of manufacturing steel. And we can see that there's some ebb and flow here over time. But in general, the amount of iron that we extract in North America has declined over my lifetime. From 1970 through about 2007 is when these data are complete. And yet we see consumption is higher than extraction, which tells us that the only way within the United States, within North America, we can satisfy our consumption of iron and steel is by what? What word would we use that's in the news all the time, that was a major theme of our previous President Trump's administration from the day he took office? It has to do with trade wars. The way that we can satisfy consumption or satisfy demand is by importing, in this case, iron and manufactured steel, or importing iron as a raw material and using that iron as a resource to manufacture steel within the United States. And the point I made is that if we look at North America top right, Japan and Korea top left, the European Union and its member countries left center, and China bottom left, we can see that all of those regions around the world consume more than they extract. And the only way for that to be possible is if each of those regions is importing iron from another region. And that's where South America becomes important, because if we look at the data for South America, we can see that in South America, extraction is significantly higher than consumption. And remember that extraction here equals mining, something I'll come back to and focus on in today's lecture and in subsequent lectures. So what you're also looking at here by way of trade is imports and exports. South America is extracting iron at a much greater rate or total quantity than South America is consuming iron. And the difference here between what South America consumes and extracts, South America exports to North America, Japan and Korea, the European Union and China. And that's a really important point that I want everybody to understand. And it has to do with the evolution of our trade routes going back thousands of years, but in this case, over the last 50 years. Now, what's important when we think about resources, and in the last lecture I talked about the years left of copper as an example. And remember that years left, what data do we need to calculate how many years of copper we have left? Well, we need to know how much do we currently produce, and meaning how much do we produce or consume, those are synonyms, and how much copper have geologists identified is readily available to extract or mine at the current price of copper. And I know I've said this and I'll say it again today, the concept of the price of copper becomes extremely important, and today I'll try and contextualize why that is. One of the things that we have to address with respect to resource consumption is human population growth. As we grow our global population, meaning more people around the world on all 6 continents, not including Antarctica, where children are born every second of every minute of every hour of every day of every week of every month of every year. As human population increases, then that has impacts on our ecological footprint as a global society. So I want to play this short video for you just to sort of set the stage.
It took 200,000 years for human population to reach 1 billion. It then took 200 years for human population to reach 7 billion. Today, our world population is near 8 billion. What caused this dramatic increase in population? The Industrial Revolution led to an increase in food production, advancements in medicine, improved sanitation, and an overall increase in life expectancy. What impact has our population growth had on our environment? Thanks to technology and machinery, Humans consume resources at an alarming rate. Each human consumes energy, food, water, space. The more people there are, the more resources we consume. Some resources that we consume can be replenished by nature. This includes water, trees, animals, and soil. Resources that can be replenished are called renewable resources. If renewable resources are consumed faster than they are replaced, they can be depleted. For example, if we hunt animals at a rate higher than they can reproduce, the species may go extinct. If we use fresh water faster than it can be cycled by nature, we may deplete our water sources. Some resources that we rely on and consume are non-renewable and cannot be replenished. Gas, oil, and coal, also called fossil fuels, are our main sources of energy. Fossil fuels are non-renewable resources that we obtain from the earth. Once the fossil fuels are used, they cannot be replaced. Once we run out, they will be gone forever. Luckily, there are renewable sources of energy, including solar and wind power. Humans have modified our Earth in ways that make it no longer suitable for many species. Our population growth and resource consumption has greatly decreased biodiversity. If we want life on Earth to be suitable for all species, including us, we need to make sustainable decisions about resource consumption.
So that's a relatively simple video, and I just want you to think about that as we move through today's lecture. And among the key words in that video is rate. And remember that the word rate is a time word. So what's really important when we think about resources, and we define two resource categories, renewable resources and non-renewable resources, is that non-renewable resources are those resources produced by nature, by natural processes, as we'll talk about today. And the rate at which nature produces those resources is much slower than the rate at which humans extract and consume those resources. So this is a very important point to keep in mind, and I'll reiterate. So here are some questions. What is meant by the term extraction? Where do humans extract resources? How do we know where the resources are located? How does time play a role in resources? So when we think about extraction, I want you to think of extraction as a synonym for mining, for production, for consumption. Anything that's extracted, whether it's copper or oil, it's extracted because there is a demand by a consumer. So when a mining company extracts a metal such as copper, it's because on the other end, my laptop wants electrons to flow across copper wire into my laptop, where copper embedded in my laptop, a direct resource, stores that charge in a battery, along with lithium and cobalt and carbon and aluminum, the other components of a lithium-ion battery. So extraction equals mining, equals production, equals consumption, equals demand. Where do humans extract resources? You know, where do we actually find the copper? Where do we find resources to extract them, right? You know now that resources literally put places on the map. How do we find those places on the map? How do we know where they are? You know, I will emphasize here, and we'll come back and touch on this in a future lecture where the entire topic is exploration for resources. If we go back to the 7 metals of antiquity that are mentioned in the Old Testament, those 7 metals existed at Earth's surface. And the way that we found them was literally by tripping over them. We could physically see them at Earth's surface. Today that has changed, and as we'll see in a future lecture, we now have to use increasingly sophisticated techniques to find resources buried below Earth's surface. And then the last question here, this gets to rate. How does time play a role in resources? How much time does it take nature to form a specific resource that we use as a copper resource? How much time does it take nature to form a resource that is enriched in aluminum such that we can extract it and we can use that aluminum? So rate and time here, think of them as synonymous. So let's think about copper, right? Copper is a metal that I use throughout this lecture, throughout the entire class. So let's think about where we source copper. How many people think that you could satisfy your consumption of everything in which copper is directly embedded, meaning a direct resource, and also the supply chain by doing this? You pick up a shovel, you walk into your backyard, or you go to a local park in Ann Arbor or San Francisco or wherever you may right now be. And you take the shovel and you just dig into the ground and you turn over the soil. But instead of turning over the soil for the purpose of planting a garden, you're turning over the soil to get copper, right? Where is the copper? Is there copper in that soil, right? How would you physically get the copper out of that soil? If we think of soil as a product of the chemical and physical weathering of rocks, we know that that soil contains 92 elements. Every element in the periodic table, all naturally occurring elements, are contained in that soil. And so therefore we know that copper must be contained in that soil. So if we just keep digging and digging and digging, do we find copper? Right? How many people think that we could do that? Well, the answer is we cannot do that. Not unless you live in some very special places on Earth. We get copper from areas such as the one shown in the photograph here. So if we break this photograph down first and we look at the right-hand side over here, this inset image, here is a person standing at a guardrail and they are looking down into a giant open pit mine. And we'll come back and go through the details of how we construct these open pit mines. But this person is looking into the open pit mine, and that mine in the inset is what you see in the larger photograph that takes up most of your screen. That particular mine is the world's largest man-made hole in the ground. It was not an asteroid. It was not here when Earth formed. We're pretty sure that this was not an omnipotent being who just grabbed a shovel and dug for a few hours. Humans dug this starting around the year 1900, and I'll walk you through that evolution in a future lecture. For now, I just want you to think about that hole, and to give you a sense of scale, right, the inset obviously shows a human adult. You can see this hole. This photograph that I'm moving my mouse around right now, that photograph was taken from the space station. So the space station is, give or take, a couple of 100 miles above Earth's surface, and an astronaut orbiting the Earth on the space station was able to use a 35mm camera with a zoom lens to photograph this particular hole in the ground. And that specific hole in the ground exists in a place called Bingham Canyon, Utah, in the western United States. So why does that hole exist? If I tell you that in 1899 there was no hole, zero hole, and humans live here, we lived here in 1899, why do you think from 1900 to 1921 we, collectively humans, have dug this incredibly large hole? Here's where that hole is located. So if we look top left, we've got a map of the contiguous or conterminous United States. Here's the state of Utah out west. Here is bottom left, a map of Utah, Salt Lake City and the Great Salt Lake up here in northwestern Utah. And this red star, if we zoom out from this box right here and we zoom following these lines and we blow up a portion of Salt Lake City, the Great Salt Lake is up here, top center. This is Greater Salt Lake City. This highway is Interstate 15 that runs all the way through Utah up into Idaho to the north. And then if you take it south, it runs by about a, give or take 6-hour drive south to Las Vegas, and then another 4-ish hours, and it takes you down towards Los Angeles. And then the inset here on the right-hand side, this red box, that is labeled the Bingham Canyon Pit. And pit here means hole, big open hole. And that pit is something that humans have dug. Why? Why would we dig that hole? Right? Were humans bored? They didn't have anything to do in 1900 because they didn't have electricity, they didn't have, video games, they didn't have music the way we have it today. It turns out that that hole, which I show you here and give you some dimensions, was dug for a very specific reason. So looking at that hole now, here are some pictures that I put together when I took a trip here a few years ago. And the hole from side to side is 4,000 meters. That's 4 kilometers, or give or take about 3 miles in diameter. And the hole from bottom to top is about 1,200 meters, or 1.2 kilometers, or give or take about 0.7 miles. So we've got this massive hole, and it exists because humans decided that we should dig into that specific spot on Earth, and that specific spot on Earth became a spot on the map. And the reason it became a spot on the map is because that is a place where nature has formed rocks that are so rich in the element copper, they are much more enriched in copper than rocks everywhere else in Utah, and everywhere else for that matter around the world. That beginning in 1900, humans began the process of the extraction of copper from those rocks. They mined it, they produced it because there was demand for copper. Remember, 1900 is roughly the period of time where we start to see the penetration of electricity throughout the United States slowly growing. We start to see the advent and penetration rate increasing for combustion engine vehicles. We know that copper is fundamental to delivering electricity. We know copper is fundamental to building engines and the electric lines that run in combustion engines. So over the last 120 years, the collective we have dug this big hole in the ground to get the rock that is enriched in copper. Well, what does that mean? If we look here again at the photograph on the top right taken from the space station, here's that massive hole, 4 kilometers in diameter, more than 1 kilometer deep. It's a huge, huge hole, the largest hole dug by humans on the surface of the Earth. Inside that hole, and prior to that hole being started, are rocks that you can see here on the bottom right. And all I want you to see in the rock on the bottom right, or the photograph of the rock on the bottom right, are these really nice goldish yellow shiny minerals. This particular shiny gold yellow mineral is a mineral called chalcopyrite, C-H-A-L-C-O-P-Y-R-I-T-E, chalcopyrite. And it's one that will come back and I'll use as the example for a number of lectures. So trust me, you'll see it. And what's important for you to know here is that this hole and the rock inside of where the hole is dug now, and the rocks at the bottom of the hole where humans are continuing to dig the hole deeper, they contain this particular mineral, chalcopyrite. But if you go to that hole and you walk south, you walk east, you walk north, you walk west, let's say you're over here west of that hole, the rocks over here do not contain chalcopyrite. The rocks down here do not contain chalcopyrite. The rocks on the right-hand side do not contain chalcopyrite. And the rocks on the north don't contain chalcopyrite. So one of the keys, the reason this hole is here, is that it contains an anomalous quantity of this particular mineral chalcopyrite. And I'll tell you why that's important. But first, I just want to make sure you understand why mining companies would target it, in addition simply to the demand for copper. The key to mining is that it must be profitable. We'll talk about the environmental issues around mining, but for right now, I want you to think about it purely from a capital perspective, a dollars and cents perspective. In order for any company to proceed digging a big hole in the ground like this one, they have to know that as they dig that hole and they extract the rock that we see on the lower right side here, that they can dig the hole and physically and chemically separate copper from this rock where it's contained in this mineral chalcopyrite, and they can do that and make a profit. So that's part of the business model. No company can exist if they lose money. So the first key to mining is it must be profitable. And in order for mining to be profitable, the rock that mining companies are digging, mining, extracting, that particular rock has to have what I say here in number 2, a higher than average concentration of a given resource than background concentrations. Well, what does that mean? In the case of copper, the copper in the rock in this hole is much higher, meaning there's a lot more copper than the copper in the rock everywhere around the hole. And one of the important things that geologists focus on is what we call the average concentration of copper, or the background concentration of copper. How much copper is in your backyard soil? How much copper is in my backyard soil? How much copper is in the soil in Beijing, or Tokyo, or Sydney, or Soweto? In each of those areas, geologists over the last 100 years have measured the concentrations of copper and every other element in the periodic table, so that we have a good understanding of what the background concentration is. And then what mining geologists do is they search for areas on Earth's surface or below Earth's surface that contain that particular resource, in this case copper, at a much higher concentration. So if we just go through some numbers here, just to give you a sense of this particular rock. The rock here, okay, which has been extracted over the last 120 years, contains about 1.5% chalcopyrite by weight. And this mineral chalcopyrite contains 3 elements. It contains copper, it contains iron, and it contains sulfur in this stoichiometric proportion: copper, iron, sulfur. Which means that the mineral chalcopyrite is about 35 weight% copper if you look at the atomic masses of copper, iron, and sulfur. The rock here at Bingham Canyon, Utah, the rock contains about 0.5 weight% copper then, which means that 20 tons of rock that we dig out of the ground contains 1 ton of the metal copper. Currently, as of February 2021, the market value of copper, meaning the dollar value of copper for copper that's bought and sold around the world, something we'll come back to, is about $6,000 per ton. At Bingham Canyon, they extract or mine 150,000 tons of rock every single day. And if you work the math out, the value of copper in that rock is worth almost $45 million. So mining can be extremely profitable as long as the abundance or concentration, in this case of copper, is much higher than the average or background concentration of copper. So why does this hole exist? This hole exists because around the year 1900, society demanded more copper. Our consumption of copper rapidly increased, and humans noticed that the rock right here was enriched in this mineral chalcopyrite, and that mineral chalcopyrite is 1/3 by mass copper, and they started digging that hole to extract the rock. They didn't dig it over here on the bottom right portion of the photo. They didn't dig it over here on the bottom left portion of the photo. They specifically targeted that rock. So before I go on to the next slide, I'm going to show you a brief video here, because if you don't remember back to high school chemistry, or you may not have taken high school chemistry, you learned something in high school chemistry that's important for you to understand the next slides.
What does it mean to be 1 in a million? Not in the greeting card sense. In the scientific sense, where 1 part per million is a unit of measurement. Parts per million counts the number of units of one substance per 1 million units of another. It can measure concentrations when a small amount makes a big difference. For example, A concentration of just 35 ppm of carbon monoxide in the air is poisonous to us. We encounter measurements like this pretty often, but because it's hard to conceptualize really large numbers, it's difficult to wrap our brain around what 1 part per million really means. So here are 9 helpful ways to visualize it. If you had 11,363 pianos worth of piano keys, one of those keys would be about 1 part per million. So would a single granule of sugar among 273 sugar cubes. 1 second in 11.5 days. Or 4 dots in the painting A Sunday Afternoon on the Island of Le Grand Jatte. Your bathtub's capacity is about 60 gallons, so 7 drops of ink would be 1 part per million. The English version of the Harry Potter series has 1,084,170 words, which makes hippogriff on page 221 of The Prisoner of Azkaban a little less than 1 part per million. A million kernels of corn is about 1,250 ears, so 1 kernel in that truckload would be 1 part per million. There are 10 million bricks in the Empire State Building, so 1 part per million would be a pile of just 10. And finally, 100 people worked together to animate this video. Collectively, they have about 10 million hairs on their heads. Pluck 10 of those hairs, and you have 1 in a million.
All right, so I wanted you to watch that just to take you back to high school chemistry if you remember these concepts. And this is the concept known as parts per million. So what I want you to think about now is comparing and contrasting that rock at Bingham Canyon that contains a lot of copper with average or background copper concentrations in all other rocks on the planet. So look at the photograph on the top right, and what do you see? You see a countertop. The countertop is made of the rock granite, and granite is a natural rock. It forms by natural processes. In that granite are all 92 naturally occurring elements, from hydrogen to uranium, and they're all present at different concentrations. If we analyze that granite rock, we would be able to measure 25 parts per million copper, which means out of 1 million atoms of all 92 elements in that rock, 25 of those atoms are copper. And so we use this concept of parts per million because copper is abundant copper's abundance is very low in almost all rocks on Earth's surface. Granite is an extremely common rock on Earth's surface. It makes up the upper portions of Earth's continental crust, and so 25 parts per million copper, it's got a low abundance. The rock at Bingham Canyon, remember I said, contains 0.5 weight percent copper. Now, you can convert from weight percent to ppm, and as I state here in writing, 0.5 weight percent is 5,000 ppm. 1 weight percent would be 10,000 ppm. So if the average granite contains 0.0025 weight percent copper and Bingham Canyon contains 0.5 weight percent copper, we can also translate those into ppm. And this line here that I'm zooming around, Bingham Canyon contains 5,000 parts per million copper. Average rock or background concentrations of copper are 25 parts per million. 5,000 divided by 25 gives us this unitless number of 200. And what that tells us right here is that that rock at Bingham Canyon, okay, this really nice rock with all of this beautiful shiny chalcopyrite, because this rock contains so much chalcopyrite, it contains 200 times more copper than the granite in your countertop. And that's a huge difference. That's a factor of 200, which is a massive difference. So if you were going to start looking for a rock to extract, to mine, to produce copper, which would you choose? Remember that the keys to mining must be profitable. And in order to be profitable, you have to mine a rock that has a higher than average concentration of a given resource or metal than background concentrations. So which one of these two choices would you go with? Would you choose to mine granite that contains 25 parts per million copper, or would you choose to mine this rock at Bingham Canyon, which contains 5,000 ppm copper? Now, everybody's going to give us the same answer, and it's a duh. You would choose the rock on the lower right. And this is in fact what geologists want to do. They want to find rock that is enriched, in this case in copper, and that's the rock that they target to mine because it contains copper at 200 times more than copper everywhere else. Within geology, there is a specific branch of geology or a subdiscipline known as economic geology. And the word economic is there strategically because the goal of economic geology is to understand how mineral deposits form, and a mineral deposit is a rock that has formed by natural processes, and that rock is enriched in one or more metals that society consumes, whether it's copper or gold or aluminum. And the economic term in economic geology, or the use of that word, is attached to the fact that economic geologists are involved in mining, extracting metals that have value attached to them by society. The geologists themselves have nothing to do with the value attached to the metals. That's something society does, and then geologists try and maintain a sustainable supply of that metal for society. So what's important is to think about how does nature go from what we call background, your soil, my soil, the average soil in somebody's backyard, your granite, my granite, the average granite. All of our soil, all of our granite contains 25 parts per million copper. In order for a mining company to be able to profit by mining rocks that contain copper, they need rocks that contain at least 5,000 ppm copper. So they need nature to have increased the abundance of copper by a factor of 200. So I've just popped a lot of stuff on the slide here, and I'm going to be quiet for about 10 seconds and let you look around. All right, that's give or take 10, enough time to take a sip. So let's start down here on the bottom left. On the bottom left is a photograph taken in the very late 1800s. And the circle here in red, I'm circling the head of a guy whose name was Frank Wigglesworth Clark. Isn't that a great middle name, Wigglesworth? F.W. Clark. And that's the Clark here with an E at the end of it. F.W. Clark was a geologist, a geochemist. He spent time at Cornell University, and then he worked for the federal government for part of his career. And what F.W. Clark did is he was a pioneer who figured out how to measure the abundances of elements in rocks and soil on Earth's solid surface that we walk on. He figured out how to measure their abundances, and he was the first person to come up with what in essence is a table for all elements in the periodic table and what their average concentration is in rocks and soil on Earth's surface around the world. And so sticking here with just the example of copper, he was able to figure out that the concentration of copper is about 25, 26, 27 parts per million. And that's what I'm circling here. That's what we call the crustal abundance, which is equal to the average concentration or the background concentration. So that crustal abundance of, in this case, 27 parts per million determined by Frank Wigglesworth Clark, that is our background concentration. Now, if you look at the row here that I'm moving my cursor across, for the element copper, we mine it primarily from one specific type of mineral deposit, and we call that mineral deposit a porphyry mineral deposit. I can promise you don't have to memorize that right now, and in fact in this class I'm not even going to go into the details of porphyry deposits, except to let you know that they're associated with volcanoes. So if the average crustal abundance of copper is 27 parts per million, according to this slide, this column here, which is called the grade, and then under it in parentheses is the word median. What the grade tells us is that if you look at all the mining companies around the world who are extracting copper, Bingham Canyon, Utah is one, and there are hundreds of other holes around the world that geologists are using to dig into the earth and extract those rocks to be able to extract the copper. The grade indicates how much copper is in the rock from each one of those mining operations, every Bingham Canyon around the world. And the data tell us that the average grade, or in this case the median grade, is 0.54 weight percent. Now remember, 0.54 weight percent is equal to 5,400 parts per million. So 5,400 parts per million divided by 27 parts per million, we get that ratio of 200. That ratio of 200 is what we refer to as the Clark value in honor of F.W. Clark. The Clark value, as I write in the bottom, is then defined as the ratio of the concentration of an element in an ore. And for ore, look at this photograph here, center right. That rock is what geologists would call ore. So it's the ratio of the concentration of an element in an ore relative to its average crustal concentration. So it's giving you a sense of the enrichment that is required for any mining company to be able to profitably extract that rock and separate the copper and provide that to society. For every element that humans consume, whether it's an indirect resource in the supply chain or a direct resource in the product that you're using, your smartphone, your laptop, your television, your car, you name it. For every element, the Clark value has been quantified by geologists. So here, this is the example of copper. And here, just as a second example, is data for vanadium, or our data for vanadium. So vanadium, if you're not aware of it, it's used, among other things, as a steel additive. But about 80% of all the vanadium that is extracted / mined / produced, about 80% of all vanadium is used as a steel additive to make steel harder. So normal steel is about 98% iron, 2% carbon. And when you think about specialty steels, for example, stainless steel, specialty steels, we produce them by adding small quantities of other metals. And in this case, vanadium is one of the most important metals that we add in small quantities to steel, where steel is still dominated by iron. But by putting a little bit of vanadium in, we change the properties of steel, which has very important purposes for the way that we use steel. So for vanadium, down here lower left, vanadium we mine from a particular type of geologic system called a layered mafic intrusion, which I'm not going to go into the details of, but that's what we refer to as this deposit type. What ore deposit type do we target to extract vanadium? Layered mafic intrusions. And the crustal abundance, remember crustal abundance equals the average background concentration of vanadium in your soil, my soil, granite that you buy at Home Depot. The average crustal abundance of vanadium is 138 parts per million. So out of 1 million atoms in the average soil or average rock, 138 of those atoms are vanadium. And for a mining company to profit by digging a hole to extract rock and then separate the vanadium out from that rock, the median grade around the world for all operating mining companies is 0.6 weight percent, which is equivalent to 6,000 parts per million, and 6,000 parts per million divided by 138 parts per million is about 43. So what does this mean when we think about the Clark value for vanadium is 43, the Clark value for copper is 200? It means, again, that for any mining company to profitably develop a mine infrastructure and extract rock for vanadium, the concentration of vanadium in that rock has to be at least 43 times higher than the average concentration of copper everywhere else. For a mining company to dig and extract rock for the purpose of copper, that rock has to contain 200 times more copper than rock everywhere else. So the Clark value, again, is giving us a sense of the natural enrichment. Remember, this is nature. The natural enrichment required in order for mining companies to extract a rock profitably. And then here is a table, and I don't want you to memorize all of this. I do want you to make sure you remember the data for copper and vanadium. And I want you to make sure you remember how the Clark value is calculated or how it's determined. But if you just look at a snapshot over here of the data compiled in this particular paper, copper, sodium, zinc, arsenic, rubidium, molybdenum, tungsten, lead, vanadium, gold, silver, nickel, right? These are all elements that are part of our built environment, either as direct resources physically embedded in the products that we use, or they are used in the supply chain to make the products available to us. Here we have in the center a list of different deposit types, and for deposit type, you can ignore these for now. Then we have this column over here for grade, and again, remember the grade here is the concentration for each one of these elements that is necessary for a mining company to make a profit. We have the crustal abundance, or the average background concentration of each one of those metals over here on the left is given in this column here. And so by dividing column A by column B, if I use the A and the B superscripts, dividing grade by crustal abundance gives us the Clark value. And take a second to look at the Clark values here, and then look back over on the left-hand side. So take a few seconds and do that. Right? I previously showed you that the Clark value for copper is 200. Down here is vanadium, and if we move across for vanadium, the Clark value is about 43. But then look at the Clark value for gold, 7,700. The Clark value for the element tungsten, 6,600. The Clark value for the element sodium. Notice that the Clark values change significantly. So for example, a mining company, in order to be able to profitably extract rock from which we can extract the metal sodium, the mining company needs that rock to contain 17 times more sodium than average crustal abundance. 17 times. In order for a company to mine, in this case, gold, down here on the lower right, a mining company needs the quantity of gold in the rock they want to mine. We need that gold to be 7,700 times more abundant than the average concentration of gold. So Clark values are specifically calculated for each resource in the periodic table. Now, what do you think controls Clark values? What controls whether or not a rock somewhere is enriched in copper or sodium or aluminum or tungsten or another metal? When we go back here and look at the photographs on the bottom of the slide, and we've got our large, what we call an open pit mine, this huge hole that humans have dug over the last 120 years. And digging that hole, we extract the rock that we see here on the right-hand side. That rock that contains 1.5% by weight of the mineral chalcopyrite. And since chalcopyrite is roughly a third by weight or mass copper, this rock is about 0.5 weight percent copper. So what geologists are interested in understanding, specifically economic geologists, is how does nature make this rock? Right? How does nature make this rock? Where does nature make this rock? You know, when does nature make this rock? And at what rate does nature make this rock? You know, why did nature choose this particular spot on the map that we now call Bingham Canyon, Utah, for this particular rock to form? Right? Why does it happen? And how long did it take? And remember, right here, when we think back to human population growth, one of the things that's really important to understand from the perspective of renewable versus non-renewable resources is if nature takes X amount of time to make this rock and humans extract and use that rock and the copper within it at a much faster rate, that means that this particular resource is non-renewable. So then the next question would be, why does this rock contain 200 times more copper than average rock? And that gets to thinking about what are the processes that nature uses? What are the recipes that nature uses, right? And here I mean the physical and chemical processes that happen in nature that allow this rock in this particular spot on the map, that put this place on the map for modern society. What did nature do to increase the concentration of copper in this rock 200 times more than the concentration of copper everywhere in the rock around that hole? How did it happen? One of the things that's also important to keep in mind here, and I've already mentioned profitability. So mining companies can only operate if they're able to profitably extract a resource. What do you think the relationship between the abundance of a resource, its price, and the Clark value for that resource is? And remember, Clark value is the ratio of the concentration or grade of any resource that is required for a mining company to extract that resource at a profit, divided by the average crustal abundance for that particular resource, gives us this unitless Clark value over here, which we said for copper is 200, for vanadium is 43, for gold is 7,700, etc. What do you think is the relationship among resource price and Clark value? So if you look at the plot here, all I want you to see is that the y-axis is concentration in Earth's crust. So low concentration at the bottom, high concentration at top. And the x-axis is price. $1 on the left side and $1,000 on the right side. Now, if you were to think about the Clark values that I just showed you, and let's go back to that table, and let me ask you for a couple of these metals. If we look at the Clark value for gold, 7,700, what do you think that tells us, or what can you infer about the ability for geologists to find rocks enriched in gold relative to finding rocks enriched in sodium or vanadium? If we look at two metals, here we've got top left aluminum, Al is aluminum, and bottom right, Au is gold. Notice that aluminum has a very high abundance in Earth's crust, right? So it's high up here on the y-axis. So it's got a high concentration in Earth's crust. And this is the background concentration. Whereas gold has a much, by orders of magnitude, lower concentration than aluminum. Which means that in anybody's backyard, if you dig up soil, or anybody's granite countertop, if you brought that into my lab and we measured the concentrations of gold and aluminum, we would be able to find that your sample contains a lot of aluminum and a tiny, tiny, tiny little bit of gold. Now look at the price. Notice that gold is far more expensive than aluminum, which tells us or allows us to infer that the price for gold is high because it has a very low average concentration in Earth's crust, whereas aluminum, the price of aluminum is much lower, orders of magnitude lower than gold, and partly because its abundance in Earth's crust is very high compared to gold. So we see this relationship here where now I've populated the figure with lots of other resources. Here we have our aluminum up here top left along with silicon and magnesium, titanium, manganese. All of these metals are present in average rock at very high concentrations. So let's think weight percent concentrations. Whereas these metals down here with gold, platinum, palladium, okay, silver, indium, these metals have very low concentrations in average rock or average soil. And as a result, if we calculate the Clark values, or we use the Clark values that are based on how much gold is required to mine profitably, how much aluminum is required to mine profitably, we can see that for gold, the Clark value, as I showed you earlier, is about 7,000. The Clark value for aluminum is 4. So the Clark value in and of itself gives you a sense of the average concentration of a metal in Earth's crust relative to how much enrichment has to happen by natural processes to profitably mine that particular rock. So gold, which has a very low abundance in Earth's crust, nature has to do some really fancy things so that it can produce rocks at Earth's surface that are very enriched in gold, 7,000 times more enriched in gold, for a company to extract that gold. Whereas for aluminum, nature still has to increase the abundance of aluminum. It has to enrich the amount of aluminum in a particular rock, but only by a factor of 4. And so we can see that the prices will vary depending on the Clark value. The higher the Clark value on average, the higher the price of a particular resource. So now I want to pivot a little bit, and we're going to transition to talking about the concept of mass transfer. And I'm going to define what that means, and I'm going to use a sequence of slides that I think all of you can relate to, even if you don't consume this particular product. So I want to talk about the mass transfer and formation or accumulation of resources in natural systems. How did all of that copper accumulate such that we have this big area at Bingham Canyon that's enriched in copper? So here's just the first one, right? To me, this looks like a nasty piece of pizza. You've got the wax paper that had been on top of the pizza. And if I were to ask you, where did all of this grease or oil come from that's on this wax paper? All of you would be able to tell me that that grease used to be on the pizza. And in fact, that grease is the byproduct of cooking a pizza with cheese on it, especially if it's got cheap cheese. God forbid you use American cheese, which is just oil. Anyway, when we cook that pizza and we heat up the cheese and it becomes liquid, some of the oil or fats will seep to the top. And then all of you know this. If you put a piece of tissue or paper on top of that pizza, all of the oil gets absorbed onto that paper, and then you throw the paper away and you eat the pizza that's less greasy. At least that's what most people do, unless you're a big fan of the grease. I'm not. This is mass transfer. This is it. This is it in a nutshell. We had oil that was on the pizza. We put a piece of paper on top of the pizza, and when we pull the paper back, the oil is now on the paper. So the oil used to be here on the pizza, point A, and now the oil is here on the paper, point B. The oil is the mass, and the transfer is exactly what you can imagine having happened if you did this. The oil has been transferred from the pizza to the paper. So we've got the mass of oil that has been transferred. Now, my favorite mass transfer by way of foods, and it's hard. I got to tell you, I love brownies and I love vanilla ice cream. Probably not much better. I also love popcorn, good homemade popcorn. Anyway, I'm going to focus you here on one of my loves, which of course now I only consume decaf. When I was your age, a lot of caffeinated coffee, but be careful with that. Anyway, what you see here, this is a photograph I took at the local Meijer on Ann Arbor Saline Road. And you've got lots of coffee beans here. And you put the coffee beans in a bag. You then buy the bag of coffee. It's $8.99 a pound. And I want you to see over here on the right is a grinder. Anybody who's made coffee knows that in order to actually produce a cup of coffee, you have to grind the coffee bean. And I want you to think about this now from the perspective of mass transfer.
Now add your ground coffee to the filter. Shake the dripper a little bit to flatten the grounds. Now it's time to pour the water into the coffee. You'll start at the center and move slowly outward using small batches of water. Don't rush it. This will allow the coffee to bloom, and the process should take about 2 to 3 minutes. now you're left with a beautiful, bold, delicious cup of coffee. Enjoy.
All right. So I know this seems simple, but I'm trying to prime you here. Notice that the person in the video has put ground up coffee beans inside of here. And then they pour, in this case, we presume hot water over the ground up coffee beans. We pre-infuse it. Oh, we let it bloom. Doesn't it sound so sexy? Like, oh, has my coffee bloomed? I'm not sure. Let me check it. Anyway, it blooms. And look at the difference here between the water going in up at the top is pure water, just hydrogen and oxygen, H2O. And then in here, sort of in our white black box, we've got ground up coffee, and the water percolates through those coffee grounds, and out the bottom, it's changed. Well, why is the coffee at the bottom different? Or let me rephrase that. Why is the liquid at the bottom different than the liquid that goes in at the top? All of you have a basic understanding of this. It's because this water up here at some unknown temperature, when it is poured into the coffee grounds here, the coffee grinds, is it ground or grind? I don't know. We'll just say into the coffee grinds here, as it percolates through there, it reacts with all those coffee grinds. And as it reacts, we have mass transfer. Caffeine has a mass. We transfer the mass of caffeine from the bean to the water. We also transfer a number of other, probably hundreds of other chemicals in a coffee bean, experience mass transfer, and as a result, at the bottom, we have the liquid that we've come to know as coffee. This is mass transfer, right? Caffeine has a mass. It's being transferred from the coffee bean to the water. Now, what controls the strength and color of coffee? Okay? If you're a real coffee snob, or if you're a coffee aficionado, I prefer to call myself the latter, you take coffee beans and you grind them, and I want you to just look at the grinder up here top right. We've got coarse, regular percolator, electric percolator, drip, auto drip, fine, espresso, Turkish. And if you've never done this, I'll just tell you that this, what I'm drawing around, this is a knob that moves just like a clock. You can move it clockwise and counterclockwise. So you can move it from coarse to regular perc all the way over to Turkish and backwards. And if you look at the bottom, this figure here that I stole from Google Images, the coffee grind chart, all I want you to see here is that depending on the way that you make coffee, that controls how finely or not finely you want your coffee grinds to be. So for Turkish coffee over here on the right, the coffee is ground extra fine. It literally has the consistency of powdered sugar. If you're making espresso, that coffee has the consistency of about table salt. If you're making a regular cup of coffee in a drip machine, then it has the consistency of about sea salt. And it gets more chunky as you make coffee in a French press. Now, what does this have to do with geology? You're probably scratching your head and having a WTF moment. I promise I'll get there. And then here, for those of you that are super anal about this, you can actually see up here at the top as you go from whole bean down the column to espresso grind. Here we have, and don't memorize this, here we can see the size of the coffee grinds changes. So notice what happens as we grind the coffee finer and finer and finer and finer. The size of the individual particles of coffee gets smaller and smaller and smaller and smaller. And that also translates to, for a given quantity of coffee, a given mass of coffee beans, a significant increase in the surface area of the coffee. And you see that here if we look at, for example, the size column and then the number of particles. So starting out with 6 whole beans, where each of those beans is 6 millimeters in size, and we've got 6 particles. If we grind those beans to what we call espresso grind, now we have 491,440 particles. Like, sweet mama, we went from 6 particles to almost 500,000, 500,000 particles. And I just want to highlight here this second to last column. Okay? What we're looking at here then as the ratio increases significantly is that means the surface area that water comes into contact with increases significantly. And the more surface area of coffee grinds allows a greater extent of reaction of the water with the coffee grinds. And that plays a huge part in determining the strength of coffee and also how much caffeine comes out. So stick with me. If you're a tea fan, I could do this for tea as well, but let's stick with coffee. So here is another table, most of which you can ignore unless you want to pause this because you're super into the data. And I just want to highlight top left for the brew method. And then if we look just at caffeine here, milligrams per liter. So that's a function of the mass of caffeine, how many milligrams of caffeine per liter of coffee or liter of water. And notice that espresso has a much higher caffeine content than stovetop espresso or cold brew or French press or pour over. And that is directly related to the size of the grinds that are used to make espresso relative to the size of grinds that are used for cold brew or French press or pour over. And the size, remember, is a function, or the surface area is a function of size. So we have more mass of caffeine transferred from the same total mass of coffee beans if we grind it smaller. Now, let's think about how this applies in natural systems. So I'm going to play a short video here, and I'll start out by telling you that you're going to look at 3 different types, in this case, not coffee particles, but natural particles. Sand, something geologists call loam, which is a mix of sand and clay, and then clay. And I want you to listen and watch what happens as water percolates through each of these 3 different types of particles.
When water is added to soil, the water we add has to pass through in-between gaps or channels in the soil particles. The speed at which water flows through the column of soil is known as percolation rate, and percolation of water depends on the particle size of the given soil sample. Let us see. For this we need 3 funnels having a cotton plug at the end, conical flasks, 20 grams each of sand, loamy soil, clay, and 3 beakers with 50 milliliters of colored water. Put the sand in the first funnel, loamy soil in the second, and clay in the third. Now pour the colored water slowly over each type of soil. Observe the amount of water percolated. After some time, pour out the water which seeps through the funnel. You see, sand has the highest percolation rate, while clay did not percolate any water. So clay has the highest retention capacity. If we observe the particle sizes of these samples, we see that the particle size of sand is biggest, followed by that of loam, and clay has the smallest size. So percolation rate through a column of soil is directly proportional to the size of the particles. A soil is a mixture of particles of different sizes. Collect 3 different samples of soil from 3 different places and compare percolation rate of water through them.
So the key I want you to think about here, as the video shows you by pouring water through each of the three of these, is that when we pour water through sand, a lot of the water percolates all the way through the sand. When we pour water through a mixture of sand and clay, less water percolates through, but some water certainly still percolates through, and we see that at the bottom. Whereas with clay, no water percolated. So there are two terms that we can use here. We've talked about particle size. There are two additional terms, porosity and permeability, which we'll come back to also later in the semester. Porosity refers to how much open space there is among all the sand grains, among all the particles that make up clay, among all of the sand and clay particles that make up loam. The porosity is all of the open space within each of these three substances. And then the second term is permeability. So the first is porosity, P-O-R-O-S-I-T-Y. The second is permeability, P-E-R-M-E-A-B-I-L-I-T-Y. The porosity is how much open space there is, and permeability is how connected all of that open space is. The sand has high porosity and high permeability, so the water just cruises right through. High permeability, high porosity. The loam has high porosity, but let's say medium permeability, so the water can get through, but not as quickly as it can through the sand. And then the clay has high porosity, meaning there's a lot of little holes and open space within the clay, but clay has very, very, very low permeability. And this is what you see as a function of the same amount of time, no water could get through the clay because it's got high porosity and very low permeability. In nature, this is one of the ways that specific mineral deposits form, is by mass transfer as water falls on the surface of the earth and percolates into the subsurface. And as the water is percolating, it's doing exactly what we saw in the video where we made coffee. Now, at the Earth's surface, this is happening essentially at ambient conditions, meaning at atmospheric pressure and atmospheric temperature for that particular region. What happens in natural systems as we go beneath the surface of the Earth? Well, as we go into Earth's crust, we're no longer at atmospheric pressure. We're now increasing pressure, meaning that the amount of material on top of us as we go deeper in the Earth, if we remember that pressure equals force per unit area, as we go deeper within Earth's crust, the amount of force increases because the mass of material above us increases. And for those of you that are espresso aficionados, you've seen this and you know this, but you may not have connected it. So what's the difference between these two ways of making coffee? On the left-hand side is a screenshot from the video I showed you a few minutes ago. And here we're at atmospheric pressure, right? We're not imposing more pressure than the atmosphere is imposing on its own. And presumably we're pouring warm or hot water through the coffee grounds. And just like we saw in the sand, right? The water percolates through all the coffee grinds. There's mass transfer of caffeine and all the other good flavors in coffee, if you like coffee. And then we see a brown liquid come out at the bottom that we call coffee. How does that differ from, on the right-hand side, this machine produced by DeLonghi? This is an espresso machine, and it looks pretty different, right? It's got something here that we use to hold the coffee grinds. And the reason that espresso is fundamentally different than, in this case on the left, pour-over coffee, is we use pressure or pressurized water to extract mass from the coffee beans. And you can see that in this video here. So if you look at the inset top left, and you look at this black holder right here, okay, and you look at where I'm tracing over with my mouse, the coffee grinds are inside of this stainless steel cup. And the water is in the machine, and what happens in the machine is that as the water heats up, it heats up inside a reservoir that has a fixed volume, and because the reservoir has a fixed volume, the water as it heats up, remember that water that heats up expands, as the water wants to expand, it can't expand because the reservoir has a fixed volume, and as a result, the pressure inside that reservoir increases. And on espresso machines, as shown here at the end of this person's fingertip, we can actually measure the pressure in units of bars, and this one shows here about, well, what are we here? About 9.5 bars. So when we make espresso, we're using not only hot water, but we're using hot, high pressure water relative to atmospheric pressure to extract the mass of caffeine and other components of the coffee bean. And you can see that play through here.
In the machine. And I use the manual button on this machine. Now the pump's on, it's sending water into the portafilter. Now it'll take a little bit for it to fill up. When it starts to fill up, the pressure gauge will go up. As you see. And where it stops, nobody knows. That one is a little under 10.
Okay, so you heard the noise.
For it to fill up, when it starts to fill up, the pressure gauge will go up.
So that noise is part of the machine making the water hot, and also because it's heating up the water in a fixed volume, the pressure increases. And so in this case, when we make espresso, among the reasons it has a lot more caffeine and is also on average, it tastes very different than pour-over coffee, is because we're extracting caffeine at high pressure and high temperature. Whereas on the left-hand side with pour-over coffee, we're only extracting caffeine at atmospheric pressure, ambient pressure, room pressure. So in geologic systems, this is extremely common. In geologic systems, what we'll see is that some mineral deposits form where we simply have hot water. The example on the lower left, we're simply doing a pour-over coffee. We've got ground up particles, we've got porosity, we've got permeability. Nature pours hot water through them, boop, the water percolates, and we're going to see that we'll form, in this case, a very important natural resource, a mineral deposit that's enriched in aluminum and has a Clark value of 4. Nature also can do something similar to cold brew. So nature can have cold water flowing through rock, and nature also, on the right-hand side over here, we can form, or not we can form, we have been able to determine that nature forms some mineral deposits by using hot water at high pressure. So let me read this statement. The same mass transfer processes operate in nature to form mineral deposits that contain one or more resources that are present in much greater abundance than average rock. Made a mistake here with my writing. You guys can flag it. In a much greater abundance, or in much greater abundance. So remember, abundance is key. That Clark value tells us that in order to profitably mine one particular resource, such as copper or gold or aluminum, we need that rock to have a much higher concentration than the average concentration. And nature is going to use mass transfer processes literally identical to making coffee in order to enrich specific parts of Earth's crust in one or more resources. Now, there are lots of ways that nature does this, and there are lots of different types of mineral deposits. This is a table from our textbook, and all I want to highlight here is that processes happen on Earth's surface, the so-called surface processes, and processes happen below the surface. And there are lots of different types of mineral deposits. There are mineral deposits that form purely by physical processes. There are mineral deposits that form by chemical processes. And there are processes that are a mixture of physical and chemical. So I have reduced this down to only a handful of different mineral deposits just to give you a sense of the way in which they form, the Wikipedia version. So let's start with aluminum. How does nature enrich aluminum so that we have a volume of rock that has a concentration of aluminum that is 4 times greater than the average concentration in Earth's crust? Here's where we start, or here's where nature starts. So just as a reminder, remember that your smartphone, you've got aluminum as the battery case, you've got aluminum as part of the screen, and then usually inside aluminum wiggles its way in. And in this case, remember, the aluminum is a direct resource. Aluminum is physically present within your phone. And also remember, aluminum is part of the supply chain, so it's also an indirect resource. Now, in the background, you see a photograph of the rock granite. It's the same granite that I showed you earlier is commonly used for countertops or floor tiles or building stones. Now, the key right now is to plant the seed that granite contains about 15% alumina oxide. Okay? So about 15% of the granite is aluminum Al2O3. Now, I can tell you that mining companies would never, at current prices, mine granite for aluminum. Never, ever, no way, no how. There is nobody at the Ross Business School that could sell a business plan to extract aluminum from granite. And I'm going to explain why. If we look at the mineral granite, so here's our photograph on the left side. The most common mineral in granite is feldspar. And it turns out that feldspar is the most common mineral in Earth's continental crust. So inside the photograph of this granite, all of these sort of pinkish orangish colors that you see are this mineral feldspar. And that mineral feldspar, if you actually look at it on an atomic level, on the right-hand side, I only want to point out that on an atomic level, feldspar has the composition potassium, sodium, aluminum, silicon, and oxygen. So these elements, potassium, sodium, aluminum, silicon, oxygen, those are the only elements that make up the mineral feldspar. And within the mineral, just as an example on the right-hand side, all of those elements, potassium, sodium, aluminum, silicon, and oxygen, are bonded with one another. And what nature does is nature, by percolating water through granite, we're going to look at how nature extracts potassium and sodium and mobilizes them and leaves behind aluminum and silicon because neither of those are soluble in water. And as a result of that mass transfer process, produces the resource from which we mine aluminum. So if you look at the left-hand side, this is just a generic soil column that I grabbed from Google. And don't worry about the ABC layers right now. Just imagine that all of these layers are filled with the rock granite. And I said that granite contains 15 weight% alumina. So let's say that we start with a rock granite. It's at the surface of the earth. And nature adds water, and on geologic timescales, hundreds, thousands, tens of thousands, hundreds of thousands, millions of years, the water that falls on the surface of that granite slowly percolates through the granite, because even though we think of granite as a rock and it's solid, it over time is susceptible to chemical and physical weathering that create porosity and permeability. So the water will percolate through the granite. What do you think happens? Well, imagine again, here's our analogy. We're taking our granite, and now we've got our granite that we've put into our pour-over coffee maker, and nature's going to pour water over that granite on geologic timescales. A process known as hydrolysis, or if we break that into its two components, hydro, which means water, and lysis, which is to break, the water that is added and percolates through the feldspars breaks the bonds that hold potassium and sodium and aluminum and silicon together. So within the mineral structure for feldspar, Each of these circles or spheres represents a different element, and they're all held together by strong bonds that allow the solid feldspar to be solid. And what nature does when water percolates through that feldspar is the water chemically reacts with the feldspars. The water and hydrogen dissolved in the hydrogen dissolved in the water chemically react with the feldspar. Elements like potassium and elements like sodium and potassium love to be dissolved in water. And so the water leaches potassium from the feldspar, but it turns out that the metals aluminum and silicon are not leached. They don't like water. So as a function of time, the water, by this process of hydrolysis or hydrolysis, notice that if we look at the top image compared to the bottom image, this is a simulation of the effects of water chemically reacting with feldspar on geologic timescales. And notice here at the top, if you follow my cursor, you can see these cracks that run north-south and these cracks that run east-west. Those cracks are the porosity and permeability through which the water percolates and slowly reacts with the feldspar and leaches potassium and sodium, literally eating away at the feldspar mineral. And as a result, we can see these big channels that form here in the bottom. And the mass transfer of potassium and sodium from feldspar to water, where water continues to percolate deeper and deeper and deeper, means that we've now removed potassium and sodium. Aluminum and silicon are not soluble in water, so they're left behind. So if we look at this again, we start with granite. Granite starts with 15 weight% alumina. We allow water to percolate through that granite on really long time scales. The water sucks out or extracts potassium and sodium. The end product is a mineral resource that we call bauxite. And here is a photograph in the background where these are big trucks, big giant earth-moving trucks that I'm pointing out here. This would be a normal truck here, like an F-150, and these are people in the center for scale. And all of this red, what looks like red dirt, if you look here at the top left, here's a person holding a sample of this red earth. That red earth is what we call bauxite. And in the center up here, we have a big piece of equipment that is scooping up or shoveling up the bauxite and putting it into a truck. And ultimately, the aluminum inside that bauxite becomes the aluminum in our cans and other parts of our built environment. And bauxite contains 45% aluminum, which is a factor of 3 more than what's contained in granite. So to summarize again, how does nature transform granite on the left with 15% alumina to bauxite on the right with 45% alumina? What would the Clark value be? It would be 45% divided by 15% equals 3. So that would be the Clark value. Now, how does it happen? Well, if we come back here to our theoretical vertical cross-section of a soil profile or a rock profile on the left, and then follow my cursor, we have depth here on this black line where the surface of the earth is the top, so the top of the rock or soil column here. Depth increases as we go down. The water is percolating through all of that granite rock. It's leaching or extracting potassium and sodium and leaving behind aluminum. And what happens, if you stick with my cursor over here, is that the insoluble elements versus the soluble elements, aluminum is insoluble in water. Doesn't like water at all. So water's percolating through that granite, aluminum looks at it and says, no thank you, and stays behind. Water's percolating through that granite, and soluble mineral matter, such as potassium and sodium, look at that water and say, what's up? I want to go with you. And potassium and sodium are dissolved in the water, and as a result, the water transports or transfers the mass of potassium and sodium to deeper levels of the system. And as a result, in this sweet spot, which we call the zone of eluviation, leaching of sodium and potassium by mass balance leaves behind all of the aluminum. And as a result of subtracting sodium and potassium and leaving behind aluminum, the concentration of aluminum is increased. And that is how nature forms bauxite. By allowing water on geologic timescales to percolate through granite, and as it percolates through the granite, it extracts potassium and sodium from the mineral feldspar. It leaves behind the mineral or the element aluminum, and as a result, the concentration of aluminum increases because now the sodium and potassium are gone. Where do you think this happens? If we go back to cold coffee versus hot coffee versus espresso, where do we think this happens in nature, and how much time does it take? Does it take 5 years, 10 years, 100 years? And importantly, how much time does it take nature to form a bauxite deposit compared with the time that it takes humans to extract and use the bauxite for our built environment? Well, here's a map of the top bauxite producers around the world. Jamaica, Brazil, Colombia, Guyana, Guinea in West Africa, India, China, Australia, and a couple of deposits up here in Russia and Kazakhstan. If you look at the map and you ignore these two deposits up here, and you focus on these others, you can see that they are spatially related to the equator. And it turns out that in nature, hot water, just as we know hot water is better for extracting caffeine and all of the good stuff in coffee, hot water is more efficient at chemically reacting with and chemically weathering granite to produce bauxite. So here is, no data yet, here is a plot where the y-axis is temperature, and all you have to think about is the bottom, temperature's hot, the top, temperature's cold. On the x-axis is the amount of rainfall, and all you have to think about is on the left side, it rains a lot, it's really wet. On the right side, it barely rains, if it rains at all, and it's very dry. And we know geologically that climate, where here we mean climate is temperature and rainfall, strongly influences weathering processes. And this whole thing that we're talking about here, the chemical reaction of water, hydrolysis, is a chemical weathering process. We know that temperature and rainfall, meaning the temperature of the water that falls as rain, strongly influence how nature produces different types of mineral deposits. We know that if we now look at the data here for different regions, if we stick with the bottom left, if an area on Earth's surface has rainfall, so it's wet and the water is hot, that hot water produces strong chemical weathering. If we contrast that to the top right, think of a place like Antarctica. In Antarctica, it's incredibly dry and it's always cold. And there are some areas of Antarctica that are actually called the dry valleys of Antarctica, where there's evidence that there has been no precipitation for about 30 million years. When it's very cold and very dry, the type of weathering that nature experiences, or that material in nature experiences, is what we call mechanical weathering or physical weathering. So down here on the bottom in text, physical weathering dominates nature where there's low rainfall and it's cold. Chemical weathering dominates nature where there's high precipitation, high rainfall, and a warm climate. And at the bottom, I tell you in text, the average rate of weathering increases a factor of 2 to 3 times for every 10-degree increase in temperature. So if we look here at the y-axis and we start at negative 10 to 0 to 10 to 20, as we go from negative 10 to 0, the rate of weathering increased 2 to 3 times. If we then go from 0 to 10, the rate of weathering increased another 2 to 3 times. 10 to 20, another 2 to 3 times. 20 to 30, another 2 to 3 times. So when we think about the formation of bauxite, and we think about where we have the majority of our resources of bauxite being mined today, it's not a coincidence that they're located near the equator, because the equator is an area on Earth where it is on average hot all year, and on average lots of rain all year long. In some particular areas like Southeast Asia, they experience the monsoon season. So lots of hot rainwater falling on the surface of the earth. And that is where nature forms bauxite. And in places around the world where we extract bauxite, right? Remember these? Places like Guinea and West Africa and other countries like Jamaica, countries such as Brazil, countries such as India and China and Australia. That bauxite, which is shown here, if you look at my cursor, all of this red on the bottom, that bauxite gets put on big, huge container ships and sent around the world, and that bauxite is then processed to physically separate the aluminum from the other elements within bauxite by processes that we'll talk about in a later lecture. And remember, aluminum is part of our built environment. Every lithium-ion battery contains aluminum. Every smartphone contains aluminum. Everything in our built environment on some level today is dependent on aluminum. We can see aluminum really having a huge impact on the manufacturing sector over the last, I'd say, 5 to 10 years. I'm going to focus on its impact on the manufacturing of vehicles. So here is a snapshot from 2015 in Dearborn, Michigan, what they call the new F-150. And if you don't know this, the F-150, the Ford F-150 truck, is the most popular vehicle in the United States of America. And I think it's been the most popular vehicle since 1977. People who have an F-150 love the F-150 and get another F-150 and another one and another one and another one and another one. Okay? In 2015, Ford began producing F-150 trucks that contain aluminum as part of the frame. Right? Now think of the frame as what's holding the bottom of the truck together. The frame used to be only made of steel, and in 2015, all of a sudden Ford said, hey, you know what? We're not going to use only steel. We're going to use a combination of steel and aluminum. Why? Why would they do that? Why would Ford just willy-nilly, hey, you know what? Let's use aluminum. The reason that they switched from a pure steel frame to an aluminum frame is that it reduced the weight or the mass of the F-150 by 700 pounds. Now, 700 pounds may not seem like a lot when we're thinking about the weight of a truck, like an F-150 here, a big four-door F-150. But 700 pounds is a lot of mass. And there's an important reason why Ford, and now we see Chevrolet and other manufacturers, using aluminum as part of the frames for their truck. So here's an example of the Chevy Silverado, bottom left, and I just want to highlight, here's a legend over here on the right. Everything that you look at in this image here that's white is aluminum. So when we look at the truck, we see aluminum doors, we see an aluminum hood, we see aluminum is the tailgate. And when Chevy Silverado started introducing aluminum into their trucks, it cut the weight or decreased the weight by 450 pounds, which is a lot of mass. So why would anybody do that? It's because the lighter the vehicle is, the better the gas mileage. So this is a figure here where the y-axis is the gallons of gasoline used to drive a vehicle 100 miles. And on the x-axis is the weight or the mass in pounds of that vehicle, what's called the curb weight. And all I want you to see, if you look at the legend, Okay, the average car is sort of this bluish color. The average truck is this, I don't know, what do you call that? Sort of yellowish brown color. And what you can see is that as a car or truck become heavier from left to right on the x-axis, it takes more gallons of gas to travel 100 miles. This here, referred to as the CAFE standard, which CAFE stands for the Corporate Average Fuel Economy, this has to do with regulations at the federal level in the United States that mandate all vehicles produced by auto manufacturers have to achieve at least 27.5 miles per gallon. Now, under the Obama administration, 2 presidents ago, the Obama administration increased the CAFE standard, and in order for companies such as Ford and Chrysler, Chevy, etc., in order to meet the CAFE standard, which means they have to reduce the number of gallons used per 100 miles, what they do is they move along these lines from right to left, and among the easiest ways to improve fuel economy, to increase the miles per gallon, is to reduce the weight of the vehicle. And that's why auto manufacturers have started using more aluminum, because aluminum weighs less than iron, and as a result weighs less than steel. So as you increase the amount of aluminum and decrease the amount of steel, you make the vehicles lighter and you get better fuel economy. And you can see this here is happening in lots of vehicles now. So on the right-hand side, these are cartoon versions or schematics of Teslas. And so you can see, all I want you to look at here is all of the gray that you see is all aluminum in the Tesla. And Teslas are all electric, but remember that all electric vehicles need batteries. Batteries are themselves mass, and so if you decrease the weight of the frame of the car, you can put more batteries into the car. And when we look at the forecast down here on the lower left, the aluminum content in vehicles is forecast to increase for exactly these reasons. It improves fuel economy for vehicles that are a combustion engine, and it also improves the amount or the distance you can drive an all-electric vehicle. And as a result, we forecast a significant increase in the consumption of aluminum. So this is one of the figures that I've shown you in the past, and I'm going to tell you here, you should know this. The amount of aluminum that we consume today is approaching 1,000% relative to the amount of aluminum that we consumed in 1960. 1,000%. And when we look at aluminum, one of the things that geologists do, economic geologists and also economists that work for mining companies, one of the things that they do is they try and gain an understanding of what the demand is going to be into the future. So here what you're looking at is a diagram that I'm going to build out over several slides, where the x-axis is 2012 to about 2080. So that's our timeline, those 70-ish years. And on the left-hand side, we've got percent. And it's the percent of two things. The end-of-life recycling rate, meaning what percent of the aluminum that we mine or extract from bauxite do we recycle and use again. And of all the aluminum that we use, what percent comes from virgin mining practices? On the right-hand side, we've got global demand and mining demand. So the first thing to look at is global demand. Over the next 50 years, the global demand for aluminum is forecast to increase. And so that's shown here, the area under the curve. From 2012 to 2080, we predict a significant increase, and these units on the right-hand side are millions of tons of aluminum. So we predict an increase from, let's say, give or take about 120 million tons of aluminum per year to almost 300 million tons of aluminum per year. That's almost a factor of 3. Now, how about recycling of aluminum? It turns out that the recycling rate right now is give or take about 60%. And the forecast is that globally, we will improve the recycling rate of aluminum to close to 70%. But notice we have a big difference here on the top right. Even if we recycle 70% of the aluminum that we consume, we still have all of this aluminum that is predicted to be demanded by society. So if recycling is about 70% efficient, where's the rest of the aluminum coming from? We still need the rest. Where is it coming from? It's coming from mining. So now I've added on here this line at the bottom, and the area under that curve is the amount of aluminum that will be produced by extracting or mining bauxite. That's where it will come from. And we can look then here at this red line as an indication of how much of the aluminum we consume will come from mining versus how much will come from recycling. And today, close to 70% of the aluminum that we consume comes from mining bauxite. But notice in the future, the amount or the proportion, the percentage of aluminum from mining will decrease as recycling increases. Now, there are many points that you could take away from this. The key thing to remember here is bauxite is the natural resource produced by chemical weathering, and that chemical weathering increases the abundance of aluminum by a factor of 4. That's its Clark value. Or a factor of 3, excuse me. It goes from 15% to 45%, a factor of 3. And even if we recycle 70% of all the aluminum that we extract, we will still need to mine the other 30%. The demand for aluminum in our built environment results in placing a value, a dollar value on aluminum. And just to give you a sense of that dollar value, currently, annually around the world, the value of aluminum that's extracted and used for our built environment exceeds $100 billion with a B, $100 billion. So there's a tremendous amount of money involved in the extraction and use of aluminum in our built environment. So now I want to transition to gold. With bauxite, we talked specifically about chemical weathering, hot water percolating through granite. Now I'm going to transition to gold, which a majority of the gold that we extract forms by a completely different process. Here's a map on the right side of your screen showing the state of California in the western United States. So we have the Pacific Ocean out here, and here's the state of California. And what you can see are approximately 13,500 dots across the state of California, which were areas that immigrants mined gold in the late 1840s, 1850s, and into the early part of the 20th century. When the gold was discovered in California in the mid-1840s, it literally set off an immigration stampede where people from around the world, Europe, Asia, Eastern United States, all traveled either by ship or by land to get to California to mine the gold in each one of these locations. And this is what gives the San Francisco 49ers their name, paying homage to the 1849 gold rush. It was an accidental discovery made at a place called Sutter's Mill, and on the lower right is a photograph of Sutter's Mill, and the mill was used to saw wood to build houses for early settlers who were moving there prior to the discovery of gold. But once gold was discovered, it truly set off a stampede of people from around the world who went to California because they could find gold nuggets or small gold flakes in the rivers throughout the state of California. You may have seen images like this in movies or print. This is an image on the left of somebody who is panning gold, and what you see here is a pan where they put sediment from the bottom of the river into the pan, and they swirl that sediment around, and when they do that, gold, which is very dense, settles to the bottom of the pan, and other minerals that are less dense than gold are swashed out of the pan, and you end up, as shown here on the lower right, you end up with only gold remaining after you pan for gold. So the question I want you to think about now is, what do you think happened to the population demographics of California after the discovery of gold deposits in the 1840s? If you think back to Lecture 1 in this class, I talked about how mineral deposits or ore deposits literally put places on the map. And if we go back to the state of California prior to the gold rush of 1849, here is the population of California in the early 1840s. And you can see by distribution of Mexicans, Native Americans, or here termed Indians, whites, blacks, and Asians, you can see that the majority of residents of California at that time were Native Americans. So I want you to think about how resources, when they put a place on the map, that also correlates to the changing population demographics. So what happens by the 1850s? By the 1850s, notice now that we have far fewer Native Americans who have been driven out of California, and we've seen a population expansion of whites from approximately 2,000 to 90,000 people. And by the 1860s, you can see approximately 325,000 white people had moved to California, all driven by the prospect of mining gold and earning revenue from the sale of that gold, where all of that gold was exported out of California. And by way of cities, on the bottom here is the population growth of the city of San Francisco in 1830, 1840, 1848. Notice 1848 to 1849 to 1853. San Francisco was the port where prospective miners came into California, those who traveled by ocean, and it was also the port where gold was exported by ship back to the eastern United States and Europe for sale. So how do you think nature formed the gold deposits in California? What is special about California that it had such a phenomenal endowment of gold in the sediments along the bottoms of rivers throughout the state? There are two images on your screen. The top image is colored, and the colors correspond to elevation above sea level. So don't get caught up in the units. All I want you to see is that anywhere that there is the color red means high elevation, think mountains, and anywhere where you see a dark blue means low elevation, and in this case the lowest elevation would be the oceans. So if we look at California, you can see that moving from the Pacific Ocean inland, we move from low elevation to high elevation. And that is shown on the cartoon cross-section on the bottom of your screen, where if you imagine walking from the Pacific Ocean onto California, you would walk up a small mountain range known as the Coastal Range, across the Central Valley, and then you would start to climb the Sierra Nevada mountains, where Mount Whitney is the tallest mountain in the lower 48 states at 4,418 meters. Now, what I want you to imagine is when water falls on the Sierra Nevada mountains here at high elevation, where does it flow? Water always flows downhill. And when we think about water flowing in streams and rivers, there are a number of different things within the water itself that are moving in that stream. So here is a schematic cross-section of a river, where imagine the surface of the river is at the top of your screen. And in the top of the water column of the river, we have what's called the dissolved load. So ions such as sodium and chlorine that are physically dissolved within the water. We have the suspended load, which consists of silt and clay, very fine-grained sediment that are able to be supported at high levels in the water column. And then we have towards the bottom of the water column what we call the bed load, larger particles such as sand and gravel and boulders. If you imagine a river, I'm going to show you now an actual video that illustrates how different particle sizes flow within a river. So keep this image at the bottom of your screen in mind And now I'm going to let this video play through, and I want you to pay attention to the particles that we term the bed load and the suspended load as the river moves towards you. Gold is much denser than water, so the density of water, if we were to weigh a cubic centimeter of water on a balance, the density of water is 1 gram, whereas the density of gold is almost 20 grams per cubic centimeter. So now I'm going to show you a video where I illustrate what happens to the velocity of water if the velocity changes. What happens to the particles that are being transported in that water? So initially we have a stream that's flowing downhill. So the mountains would be to our left and the oceans would be to our right. And now we put an impediment in the flowing stream. And notice what happens. Immediately upstream of this impediment, the velocity of the river decreases. So it was flowing fast, now there's an impediment. And notice that because the velocity of the water decreases, the sediment that had been transported as This is the key to the formation of what we call placer gold deposits. So imagine if you look at the cartoon cross section on the top of your screen, imagine that we have a mountainous area with a valley. And at the base of that valley, we have a stream that in this case would be flowing from the computer screen towards you, as indicated here on the lower left, where the arrows indicate the direction the water is flowing. Now, if you could actually stand in that water and you could measure the speed or the velocity at which water is flowing, you would find that water flows the slowest along the base because of friction between the water and the underlying rock, and it flows the fastest towards the top of the water column. It again flows slow right at the surface because of friction between the water and air. As you change the profile of the river, the velocity will change accordingly. And what happens, if you focus your eye on the image on the lower left side of your screen, is that in rivers that are not straight, so rivers that have curves or meanders, as the water moves from top to bottom in this river, it moves fastest on the outside of the meander, and it moves slowest on the inside of the meander. So the yellow here on the inside of the meander is what we call a point bar, and that is where sediment falls to the bottom of the water because the velocity of the water here on the inside of the meander decreases and becomes so slow that the river can no longer carry that bed load or dissolved or suspended load. This is where placer gold deposits form. So if you look at the image here, where water is flowing from top to bottom, what you can see is that as the water flows from top to bottom, on the inside of each meander belt, where the velocity of the water is slowest, that is where gold settles to the bottom of the water column, remaining there as the water continues to flow downstream. When this happens on geologic timescales of hundreds of thousands to millions to tens of millions of years, this is how nature is able to accumulate significant quantities of gold throughout the river systems, not only in California, but throughout the world. So when we look again at the map on the left side of your screen, at these 13,500 dots that represent places where gold was mined by immigrants to California in the middle and latter part of the 19th century, each of those dots corresponds to a place, if you look now on the right side of your screen, where stream water was eroding and transporting gold from the Sierra Nevada mountains, which are shown here in the background schematically. And as that gold was being transported downstream, along the length of the river, that gold would settle to the bottom of the stream when that stream velocity decreased on the inside of meander belts. Now, it turns out that the discovery of gold in California in the 1840s was extremely important, not only for putting California on the map, but it was important because it became the primary source of gold produced by the United States for much of that century. So here is an image showing gold production on the y-axis relative to time on the x-axis. And all I want you to see here is that the gold that was produced after that discovery in 1849 was almost 30 million ounces of gold, which immediately made California a destination for people to move to get access to that gold because it was a source of revenue. And if we look here at another one of these plots where we see change in production on the y-axis versus time on the x-axis, all I want you to see is that relative to 1960, there have been some ups and downs, which we'll talk about later in the course. But currently, globally, our society consumes about 125% more gold than we did in the year 1960. And that gold that we consume is worth a significant amount of money. So here is a histogram where I only want you to focus on the left side, gold. And you can see that on average, each year, the value of gold that is mined and sold around the world exceeds. Okay, so after placer gold deposits, let's transition to another resource that is probably one all of you enjoy. Certainly has led to a number of public health crises when we think about the effect of too much salt on the human body. We use it as a preservative for fish on the bottom here. It's what we think of as table salt. And table salt is specifically a mineral that geologists call halite, H-A-L-I-T-E. And I want to talk now about how nature forms thick sequences of halite that we use as our resource for table salt. On the right-hand side over here, I can tell you, is a great book. The title might not seem super sexy and may not be a beach read, but it's really a great look at salt, and it goes through the history of salt going back to biblical times, thousands of years ago, and how trade routes evolved around salt, and how critically important salt was to the expansion and evolution of global trade routes in the 14, 15, 16, 1700s. It's a great read if you want something for a good weekend to read. So watch what happens in this video. We're pouring a liquid, and you can think of that liquid as water. And then we're pouring a solid, and that solid is halite, or what we think of as table salt. And we're now stirring this mixture of halite and water. And what happened? Right? What physically, what chemically happened? You saw this with your own eyes, right? We pour water into the glass. We put solid halite, right? Here's our solid halite that we're pouring into the water. And then we stir. And what happens? Where did the halite go? Well, it disappeared. Now, granted, you can see a little bit of halite in the bottom, but the majority of that halite has now disappeared. What does it mean when I say it disappeared? Where did it go? What happened to it? What happened to that halite is that it dissolved. And at some point in middle school or high school, you probably had some chemistry lectures about the process of dissolution. And I just want to review some of those very basic ones here. So on the image on the lower right, we've got a container of Morton sea salt. All right, excuse me, this is not Morton sea salt. This is Morton table salt. It's much finer grained than sea salt. And that sea salt is the mineral halite. And the mineral halite has this chemical formula, NaCl. Na is the element sodium, Cl is the element chlorine, and in this case, sodium and chlorine are ionically bonded by electron sharing, and they produce the solid sodium chloride halite. But we all know, you've all done this in your kitchens at home, or you've seen somebody do it. If we take halite, sodium chloride, and pour it into water and stir, then the halite dissolves. And what does it mean to dissolve? It means that as we go from left to right up here at the top, we start out with solid halite, where sodium atoms are ionically bonded with chlorine atoms, and we can see this structure. It's an infinite number of sodium and chlorine atoms bonded to one another. And what happens when the halite is put into the salt, and with or without stirring, but stirring speeds up the reaction, the water separates the sodium and the chlorine atoms, and the water molecules, these sort of Mickey Mouse hats right here, they essentially shield the sodium and chlorine atoms from one another, and that's the process of dissolution. And it looks like this on an atomistic
ionic
level.
substance, such as sodium chloride, is
Let me back that up. So here's
when
what it
an
looks
ionic
like.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
So that's all I want you to see there, is that the water molecules chemically interact with halite. The water molecules strip the chlorine and strip the sodium apart from one another, and then they essentially create shields around each of those molecules. So here on the left, we've got water molecules 1, 2, 3 in the background, 4, and they are surrounding this chlorine atom. And on the right-hand side, we've got a sodium atom in here, and we've got 1, 2, 3, 4, 5, 6 water molecules surrounding the sodium atom. And when we think back to charges for elements, chlorine is commonly an anion, so it has a negative charge. Sodium is a positive ion, a cation, and so the positivity of sodium attaches to oxygen in red, which is negative, and the negativity in chlorine attaches to the hydrogens in white that are positive. Positive and negative balancing each other out. That is dissolution of NaCl in water. Now, imagine that we dissolve salt in water and we leave it on the counter for human timescales and geologic timescales. What happens? At the beginning of this video over here, we have the water that was in that glass where we started out with pure water, we added halite, we stirred, and the process of dissolution broke the ionic bonds between sodium and chlorine such that now in the water we can't see the halite anymore because all that exists in the water, in addition to the hydrogen and oxygen that make up the water molecules, sodium and chlorine exist as individual elements surrounded by water, and we can't see those. But now imagine that we put that water on the counter and we walk away for 1,000 years. What's happening in this video? What are you watching? What you're seeing here is the result of the water evaporating, and as the water evaporates, sodium and chlorine do not evaporate. As the water evaporates, all of those water molecules that previously shielded chlorine from sodium, when those water molecules evaporate and are no longer inside our petri dish or the container, the sodium and chlorine, they come back and ionically bond with each other again, and they precipitate, after they've ionically bonded with each other, they precipitate or crystallize as halite. So this is a very reversible process. We can fill a container with water, we can pour halite into the container, we can stir the water plus halite mixture, the water molecules will chemically react with halite and they will dissolve halite by breaking the ionic bond between sodium and chlorine. And if we evaporate the water, so the H2O molecules now undergo mass transfer from inside of this petri dish back to the atmosphere, sodium and chlorine reform their ionic bonds by electron sharing and crystallize as the mineral halite. And that's what this time-lapse video shows. And you can do this at home. You may in fact have done this. You know, if you have a glass and you fill it with water and you stir in salt and the salt dissolves and you put that glass on the windowsill for a day, a week, a month, when you come back, the water has evaporated and you'll see a little bathtub ring of salt around the top of the water column within the glass. And that salt is the crystallization of halite caused by the evaporation of water. Now this happens, and it has happened on geologic timescales around the world. And the water that we're talking about now is water in our oceans. It's not water in the Great Lakes. For those of you from the Great Lakes area, you know, we love to talk about the t-shirts and how the Great Lakes are salt-free and shark-free. So we're not talking about water in the Great Lakes. But I want to contextualize this in terms of the supply chain for salt. Now, when you hear this term, and I'll circle this up at the top, rock salt, that rock salt is halite. It is that mineral sodium and chlorine, sodium chloride, that we geologically define as halite, and we commonly refer to in society as rock salt. And each of these red dots here is an area where humans mine or extract rock salt for the purpose of consumption by humans. Either consumption because we eat it, we add it to our food, or consumption because we use it as a de-icer by spreading it across icy and snowy roads in the wintertime so that we decrease the melting temperature or we decrease the freezing temperature of water. So I want you to make a connection here with supply chains as well. If you go to the city of Detroit, you can get on an elevator. Well, you can't just get on the elevator, but if you go to the city of Detroit and you get permission, you can actually get on an elevator that drops 1,160 feet beneath the city of Detroit. And if you look at my cursor over on the right-hand side, when you step out of the elevator, you step out and you see these thick white layers of rock to the left and to the right and behind the elevator shaft. Those thick layers of white rock in this cartoon version here on the right are what you see on the photograph on the left side. These thick layers of white rock are composed almost entirely of the mineral halite, or table salt. And the Detroit Salt Company exists solely for the purpose of digging this deep elevator shaft, 1,160 feet deep, and then extracting that rock salt, bringing it back up to the surface where we consume it. That's the beginning of the supply chain of salt in Detroit. There are a number of places, as I showed you on the previous slide, and here you can see the 7 dots. One of them here is offshore Cleveland. Now, initially you might have a WTF moment. Offshore Cleveland is this body of water called Lake Erie. How can we mine salt from Lake Erie? Well, we're not mining it from Lake Erie. What we're doing here, identical to the way the Detroit Salt Company mines, is the mining company has built an elevator shaft that goes hundreds and hundreds and hundreds of feet below the city of Cleveland on dry land, and then they dig tunnels into the rock beneath Lake Erie, and that rock is rock salt containing the mineral halite, and they extract that halite and bring it back to the surface. And I'm going to show you a video here to give you a sense of that process.
When Old Man Winter rears his icy head, there's one thing that keeps Ohio from becoming a virtual slip and slide. Salt. A natural deicer, over 17 million tons of rock salt was spread over roads and sidewalks in the United States during the particularly fierce winter of 2015. But where does it all come from? The answer might surprise you.
Right now we're in the Whiskey Island mine, 1,800 feet below Lake Erie. We're mining salt for the purposes of road de-icing. Last year we mined a little over 3 million tons in a pretty mild winter. In a normal winter we'll do about 4 million tons a year.
Ohio is one of the top exporters of salt in the country, and it's actually mined right under our noses in places like Cargill's Whiskey Island Salt Mine. The 12-square-mile mine lies just offshore of downtown Cleveland. Lake Erie is the shallowest of the Great Lakes, with a depth of about 56 feet near Cleveland. The salt mine lies about 1,800 feet under the lake.
One of the reasons we mine under Lake Erie is because of only having to deal with a single landowner, which is the state of Ohio, versus under land you're dealing with multiple landowners of different pieces of property. We use a conventional drill and blast method of mining. Once we blast the salt out of the ground, we go ahead, scoop it up, and put it on the belt lines to be sent to the mill for processing.
A system of conveyor belts and elevators bring the salt to the surface. Left behind are gigantic pillars of salt. These support the weight of thousands of feet of rock and lake above the mine. Engineers like Bob calculate the size and number of pillars needed to keep the mine safe.
As an engineer, in a typical scenario, you get to kind of choose materials and build what you want. An underground operation, what you have is the earth, and it's a fun and interesting problem.
But wait, let's back up a minute. How did all this salt get here, almost 2,000 feet under Lake Erie? To answer that question, we headed to Cleveland's Museum of Natural History to talk to expert Harvey Webster.
Well, it turns out that there's lots of rock underneath Lake Erie. And if you started digging at the bottom of Lake Erie and you went through the sediments, you'd come to a variety of rocks, shales, things that you would see in any kind of river cut. But as you go further and further down, you start encountering rocks like limestones. If you get 1,700 feet below Lake Erie, you will encounter a formation of rock salt. It's called the Salina Formation, and it's actually layers of salt and other kinds of rocks that have one thing in common. They were produced by being in a shallow sea, an ocean 408 million years ago. When we think about what Ohio was like back in the Silurian period, 408 million years ago, it turns out it was wet. We were under a shallow sea. And all of the rocks that underlie the city of Cleveland, no matter how deep you go, they were all deposited in water. Now, the curious thing is we always think, well, Cleveland, Ohio has always been north of the equator. It's been in a temperate location kind of forever, right? And the answer is no. It turns out that North America, like all the other continents, has moved across the planet. And at the time of the Silurian, 400 million years ago, Cleveland, Ohio would have been about 1,000 miles south of the equator in shallow tropical conditions.
So Ohio was tropical. Oh yeah, and covered in a shallow sea. And its inhabitants are not the kind of thing you see strolling in downtown Cleveland today. Eventually, these tropical conditions and some overgrown coral reefs cause the sea to dry up, leaving the salt behind.
It would get saltier and saltier and saltier until finally the salt literally settles right out of that water and forms rock salt. And this happened thousands, tens of thousands of times. And each time it happened, it would add a new layer to the rock column. And so if you went to the Cargill mine, when you look at the walls, you'll see these alternating bands. Each one of those layers is like a chapter in the history of the world, right here in Cleveland, as it existed 400 million years ago.
The salt mine looks like another world, and it really is one. It's the remains of a world that existed long before man. But even if you never get down to the mine, you'll still see pieces of this world scattered on icy roads all winter long.
Yeah, so that's a pretty good video that does a good job of giving you a sense of the mining of rock salt in literally our own backyard. And just to reiterate a couple of the points in that video, one of the things to remember about Earth is we are a dynamic planet. And when we think of Earth's continents, we think of them as stationary, but in fact they're moving. And Earth's continents move at about the same rate your fingernails grow, typically about an inch a year or maybe 2.5 to 3 centimeters. So they're not moving quickly, but nonetheless they're moving. And remember that the Earth is 4.5 billion years old. So on geologic timescales, over hundreds of millions to billions of years, the Earth's continents move around. 400 million years ago, if we look at the photograph on the right, 400 million years ago, where I've outlined the state of Michigan here in black, notice that all of the Lower Peninsula, or almost all of the Lower Peninsula, was completely covered by ocean water. Completely covered. And the ocean that we think of down here south of what is modern North America, and notice 400 million years ago, there was no Central America. There was no land bridge that connected North America, Central America, and South America. There was open ocean between North America and South America. And most, if not all, of the Lower Peninsula and much of northern Ohio and parts of Ontario and Pennsylvania and New York were covered by a salty ocean similar to the modern-day Mediterranean Sea. And over geologic time scales, or over geologic time, this is what happened. Exactly what I showed you a few videos ago, where as that ocean water evaporated, we have the mass transfer of water from the oceans to the atmosphere. And when we lose the water from the oceans, as a function of how much water evaporates, if we look at the image here on the top left and just focus on my cursor, after about 86 to 94% of the seawater, the water has evaporated, the elements sodium and chlorine will ionically bond with one another to crystallize as the mineral halite, which we know as rock salt. So this simple process that we observe here in the video of the Petri dish, when we go back hundreds of millions of years, is exactly what happened over and over and over and over again. And as it happened, each time the water evaporates, and evaporates about 86 to 94%, halite precipitates, where precipitate is the same as crystallize. Halite precipitates, and because halite is denser than the little bit of water in which it's crystallizing, it sinks to the bottom of the water column and forms these really thick sequences of salt that they show in the video here. So when he talks about time, this again goes back to rate, where this is happening iteratively on geologic timescales, and the net result are these thick sequences of halite below the ground that we build elevator shafts 1,800 feet deep. We dig up the rock salt, we crush it, and it ends up at Kroger and Safeway and Smith's and Meijer and Trader Joe's, and it also ends up at Lowe's and Home Depot as the salt we use to de-ice. Now, salt is a big business. So if we look here, this should say up at the top, agriculture and industrial minerals. Not sure why I truncated industrial. But just to give you a sense, again, here's billions of dollars on the y-axis. Salt, globally, is a commodity. It's something bought and sold. It's extracted by mining companies because society demands it, society consumes it, and salt is on average worth globally somewhere between 10 and 20 billion with a B dollars per year. And when we look at our consumption of salt, today we consume more than 200% more salt per year than we did in 1960. And you think, well, how and why? Well, for one, we've got significant population growth, back to the video at the beginning of the lecture. And as more people consume more food and salt is used in cooking and as a preservative, that means the demand for salt increases. If we go back to 1960, that's when within the United States we first started building at the federal level our current massive highway infrastructure all over the country. And what happens when we drive on the roads in the winter where it snows and gets icy? We see the trucks out and they are spreading salt. And the reason they're spreading salt is the salt helps keep water in a liquid state, so it prevents the water from freezing and forming ice and snow. And so for those reasons, we see a significant 200% increase in our salt consumption every year relative to 1960. Okay, so we've talked about bauxite, from which we extract aluminum. We've talked about placer gold deposits, from which we extract gold. And we've talked about the formation of rock salt, simply by evaporation. Well, simply on geologic timescales. So now I want to talk about the last resource in the class here that I want you to be familiar with. Certainly one that hits close to home for reasons that I'll reveal. And I want you to look at the bottle first. And I'm going to play a video, and I want you sort of in your own mind, and if you're taking notes, great. I want you to describe what you see happening, and then I want you to ask yourself, why is this happening? And as you watch, this is where you have to be patient and just let it happen. Nothing's going to jump out and bite you. What do you see happening? Right at the beginning of the video, you could see what appeared to be a bottle of water, and inside the bottle of what you might think of as water, there are a couple of different types of beads. Maybe these are the beads you make friendship bracelets out of, or some other craft project. And you've got white beads and blue beads. And I shook the bottle up really vigorously, and then I set the bottle down on my counter. And then I just let it sit. And what you're seeing here is what geologists would call differentiation. You're seeing movement of things. You are seeing mass transport, mass transfer. But I want you to think about what you see and why you might be seeing it. It turns out that in this bottle there are two liquids and there are two different types of beads. One of the liquids is isopropyl alcohol. The second liquid is a brine or salty water that contains about 10 weight% dissolved salt. So just like we showed in the video earlier, we have dissolved, or in this case, I have dissolved about 90% water, 10% salt to make a salt water solution. And then I put the isopropyl alcohol, the salt water, and the 2 beads in the water bottle. And what happens? You know, initially all the white beads immediately go to the top. All the blue beads immediately fall to the bottom. And the 2 liquids, the salt water and the isopropyl alcohol, they're in the middle of the bottle. But as time progresses, the white beads sink, the blue beads float, and this is their final stable configuration. The final stable configuration is the top of the bottle is filled with isopropyl alcohol. The bottom of the bottle is filled with salty water. And then we have the blue beads that sit underneath the white beads. So we go salt water, blue beads, white beads, isopropyl alcohol. Now I'll tell you that this is sitting on my countertop at home. The top is obviously up and the bottom is obviously down. Okay? Why does this happen? Right? What is one word that you have heard, whether or not it's in a science class or you just have heard this word? What's a word that you could use that might offer a plausible explanation for why you see this type of differentiation happen? And I'll give you a clue. It's a word that starts with a D, and then it's got an E, and then an N, S-I-T-Y, density. In this case, we have 4 different substances. We've got isopropyl alcohol with the lowest density. We've got white beads with the second lowest density. Then we have blue beads with the third lowest density. And finally, we have the salt water, which is the most dense. So what we're looking at here is separation of these 4 substances based purely on the difference in density between the 4 substances. After I shake the bottle, the isopropyl alcohol, which is the least dense, moves to the top. The salt water, which is the most dense, moves to the bottom. And then the blue beads, which are a little bit less dense than the salt water, they float until they're on top of the salt water. So the salt water essentially ends about right here. And then above the blue beads, we have the white beads that sit on top of the blue beads because they're less dense. And above the white beads, we have isopropyl alcohol. So in this column of water, here's our water bottle, and this is our column. We have 4 substances, and they have separated from one another based on the difference in density among the 4 substances. So how does this work in nature? On the left side, you've got a photograph of a volcano. And we're not going to go into the nitty-gritty details of how volcanoes work. All I want you to think about is a volcano that you may have seen on the news or in a movie. And trust me, in the movies, they always get it wrong. But nonetheless, think about a volcano that you've seen. All volcanoes, the lava that erupts at the surface, all of that lava originates before the eruption in what geologists call a magma chamber. And magma is a synonym for lava. The only difference is we call magma that erupts on the surface lava, and lava that has not erupted because it's below the surface, we call it magma. And chamber you can think of as a volume. Think of it as a big bathtub. So below all volcanoes before they erupt, there is this big chamber or big bathtub that is filled with magma. And magma is liquid rock. So it's extremely hot. And the colors here, I only want you to see that within the magma chamber, all of the yellows and sort of peach and orange and red, imagine that all of this is liquid. And what happens during a volcanic eruption is that the liquid magma for reasons we're not going to go into in this class, the liquid magma, it moves up to the surface and erupts out of the volcanic edifice at the surface of the earth or on the surface of the earth. Now, in the magma chamber, it's liquid. It's not a solid rock, it's a liquid rock. Literally here, I want you to think of liquid like bath water, liquid like any other liquid that you know. Inside that liquid, we've got all 92 naturally occurring elements, everything from hydrogen all the way up to uranium. So on the left-hand side is that same cartoon schematic where we have our magma chamber. And on the right-hand side, I show you just the magma chamber here without the volcanic edifice up at the surface or the rocks around the magma chamber. And all I want you to see here is that within the magma chamber, we have liquid magma that is extremely hot. So all of this is a liquid. There is no solid. Now, in nature, what happens to magma is that on geologic timescales, hundreds, thousands, tens of thousands, hundreds of thousands of years, this liquid magma that is initially very hot, and by hot, here we mean in excess of 1,000 degrees Celsius, extremely hot. The liquid magma will lose heat to the surrounding Earth's crust. And as it loses heat and cools, meaning the temperature decreases, as the liquid magma temperature decreases, it will start to crystallize different minerals. And it's a process that's almost identical to the one I showed you a few minutes ago, where when we allow salt water to evaporate, the sodium and chlorine ions ionically bond and form salt and sinks to the bottom. The same thing happens in magma chambers. So in nature, when we start out, or when nature starts out with hot liquid magma, and on geologic timescales that magma cools and becomes a solid, it becomes a rock like the one I show you on the right-hand side. So we go from an initial state of hot liquid magma to a final state of solidified magma or rock. Now, in some magma chambers of a very specific composition that I'm not going to go into in this class now, there are different minerals that form, and among the minerals that form, two of them are called, one is called chalcopyrite here, which I introduced earlier. Chalcopyrite was that mineral that we see in Bingham Canyon. The mineral chalcopyrite, and a second is the mineral magnetite. Now, chalcopyrite contains copper and iron and sulfur, and society desires chalcopyrite because of the copper it contains. Magnetite contains iron and oxygen, and the iron society desires because we extract magnetite and use the iron to produce steel. So both of these are extremely important minerals as part of the supply chain for our built environment. Now, magma chambers are mostly liquid. So the question I ask here at the top is, if two minerals, A and B, exist in a magma chamber, and in this case, those two minerals are chalcopyrite and magnetite. And remember, a magma chamber is a large volume of molten or melted rock. If mineral A is less dense and mineral B is more dense, what happens? And in the case of chalcopyrite and magnetite, if chalcopyrite is more dense than the magma, the liquid, and magnetite is more dense than chalcopyrite, think back to this bottle experiment that I showed you here. What do you predict will happen? What will happen to the magnetite? What will happen to the chalcopyrite relative to the liquid? Where the density of the liquid is 3, the density of the chalcopyrite is 4.1, and the density of magnetite is 5.1. What we know, or at least we've never been in a magma chamber to witness this with our own eyes, but what geologists have deduced as the most plausible explanation for what happens is because of the difference in density, dense crystals, such as chalcopyrite and magnetite, when they crystallize as the magma cools, they sink to the bottom because they're more dense than the liquid magma itself. And there also are some crystals that have lower density that will float exactly what I showed you in that bottle that I shook up. The dense crystals sink, and notice here that within this volume of magma, all of these black crystals that are dense, all of these shapes here, notice that out of a very large volume of magma, if all of those crystals are dense and sink, they accumulate on the bottom of the magma chamber, and they form very thick layers that contain only that particular mineral. They form very thick layers of, for example, only magnetite, or only chalcopyrite, or perhaps layers where we have magnetite and chalcopyrite sits directly on top of magnetite, only because of the difference in density. That's what allows the more dense minerals to sink through the magma, which has a lower density than the minerals. Now, one of the important things here, let me go back to this concept of rate and time, is that this is happening on geologic timescales. Hundreds to thousands to tens of thousands, hundreds of thousands of years that nature takes for this process to happen. And over the course of geologic time, it has happened in many places around the world. So I'm going to show you a video now that some collaborators of mine at the University of Hanover in Germany put together, where instead of using a water bottle like I did, they actually made a bottle out of fused quartz. So I'm outlining here, this is the side of the bottle on the left, the other side of the bottle on the right, and you can't see the bottom down here or the top up here. So they've got this super high-tech bottle made of fused silica, which melts at something like 1700 degrees Celsius. And they put inside of that bottle a magma, and they melted it. They heated it up to, in this case, I think it's about 1,200 degrees. And now that they have a liquid magma in here, before I play the video, I'm going to tell you to train your eye up here on the top right. So this is the top surface of the liquid magma here up at the top. And the whole column here that I'm moving my cursor through is all liquid. And they're going to drop, literally with forceps, they're going to drop crystals of magnetite right here on the surface of the magma. And I want you to watch what happens. Look at that crystal of magnetite over here on the right. Here's another crystal of magnetite. Now, the magnetite is more dense than the liquid magma, and as a result of the density difference, the magnetite is sinking through the liquid magma. The long black tail that you saw there, here, that long black tail is actually the magnetite starting to melt into the magma. And so, as it's trying to sink because it's more dense than the magma is also transferring energy or heat to the magnetite, which breaks the bonds between iron and oxygen. And as a result, the magnetite starts to melt. But the key takeaway here is that because magnetite is more dense than the magma, it sinks through the column of magma. Now, in nature, when this happens, it can produce really thick sequences of individual layers of magnetite that you can see here. So this is an area, focus on the right-hand side first, where in the image at the top right, here are two humans for scale, and they're standing in front of a layer of rock that is almost pure magnetite. And remember, magnetite down here on the bottom is a mineral that contains iron and oxygen, and it has a density of about 5 grams per cubic centimeter, so mass per unit volume. And if we then zoom in on the area that these two geologists are looking at, we can see that the layers contain lots of cycles of magnetite plus other minerals. And these are extremely important as sources of magnetite. And we extract the iron from magnetite, and we use that iron to make steel. And steel is fundamentally the backbone of our modern society. Where these pictures are taken is in South Africa. So top left, here we have a map of the southern tip of Africa. Here's the country South Africa here. And then in the circle up here, where we have this BIC, BIC stands for the Bushveld Igneous Complex. And you can think of igneous as a synonym for magma here. The Bushveld Igneous Complex, if we look at the scale, the distance from this side of the black line to that side of the black line is 80 kilometers, or give or take 50 miles. So everywhere within this red dotted area, that distance indicated here is 80 kilometers or 50 miles. And all of these red dots are areas that either are currently being mined for elements such as iron or platinum or vanadium or other resources. And the reason that these mines exist is that about 2 billion years ago, 2B billion years ago, this area was a massive magma chamber. And it was a massive magma chamber, a huge volume of liquid rock. And as that liquid rock cooled and it lost energy to the surrounding colder earth crust, minerals like magnetite and chalcopyrite crystallized and sank to the bottom because of density differences. And that process on geologic timescales has produced, in this case, one of the world's largest resources for elements such as iron and platinum and palladium and others that are contained in minerals such as magnetite and chalcopyrite and other minerals, oxides and sulfides, in this particular place on Earth. And for this exact reason, it has put the Bushveld Igneous Complex on the map for modern society, because that is a primary source of these metals for our built environment. We also have a mine in northern Michigan. So the map up here, top left, here's Michigan, here's the, what do we call it? Here's the mitt and here's the thumb, and here's the Upper Peninsula. 30% of the landmass of Michigan, 3% of the population. It's a paradise. You should all go up there. Well, maybe not all of you go up there at one time, but go up there, staggered. The yellow dot up here is an area, a city called Marquette, Michigan. And Marquette, Michigan is the home now to a mine that, if you've read the text in red here, is called the Eagle Mine. And the Eagle Mine is a mine where geologists drive down into what had been a magma chamber more than 1 billion years ago. And in that magma chamber, the density difference between magnetite and chalcopyrite and the liquid magma, or the melt, as I use the term here, caused all of the magnetite and chalcopyrite to sink to the bottom of the magma chamber. And as a result, we now have access to that fossil magmatic system, and we can extract or mine only the chalcopyrite. And in this case, the reason the chalcopyrite at the Eagle Mine is so important is that it is enriched in the metal nickel. And nickel is fundamental to our built environment. So just a little bit of, well, it's not even a tangent. I've taken a few student groups up here on field trips, and I was in Marquette, Michigan a few years ago, and walking around Marquette, Michigan, I happened to see this bumper sticker. Michigan, say no, right? Big capital letters, say no to sulfide mining. Wisconsin did. Keep that in mind later in the semester. You'll learn something about Wisconsin. So here's a bumper sticker on a car, nonetheless, that says, say no to sulfide mining. Now, sulfide, chalcopyrite, is a mineral that is part of what we call the sulfide class or the sulfide family of minerals. So sulfide here and chalcopyrite you can think is synonymous. And sulfide is the mineral within which nickel is contained that the mining company extracts. So then you back out, and of course it's a Subaru, right? If you've got a Subaru, I love it. Here's a Subaru, and of course it says say no to sulfide mining. And you look around the Subaru, and immediately what I'm drawn to is I say, here's a little bumper sticker for a canoe, and canoes are made out of aluminum and steel. Aluminum is mined from bauxite, and steel is mined from magnetite. We've got a big back window here made of glass, and glass is made from mined silicon and sodium and potassium and lead and calcium. We've then got plastic up here and plastic over here. Plastic is a byproduct of mining oil. And then over here we've got a luge. And if you're a luger, great. Definitely a bougie family here who can luge. If we've got a luge is made of steel. And in fact, the whole car is literally an amalgamation of 60 to 70 elements in the periodic table. And so I had to chuckle and I took a picture, because if you really say no to sulfide mining, you cannot have a Subaru. Sulfide mining is fundamental to our built environment as we know it. And when we look at an element such as nickel, which is mined from the Eagle mine, the Eagle deposit on Michigan's Upper Peninsula, we as a global society consume about 500% more nickel every year than we did in 1960. And there are lots of reasons for that. Among them, population has increased significantly over the last 60 years. But more importantly, even as population grows, we see that nickel use continues to grow at about 4% per year, and that's because of all of the things, all of the stuff in which nickel is contained. Nickel is part of our smartphone. Nickel is part of your headphones. Nickel is used in the production of stainless steel. Nickel is used in the production of a Tesla or a Prius. And ding, 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 nickel is used in the production of a Subaru, and nickel is mined from sulfides. And if you don't mine sulfides, you cannot drive a Subaru or any other vehicle known to mankind. So when we look at the periodic table, what I want you to focus on here are just the elements where there are circles that are colored. And when you look at all of those circles, those are all of the elements that we find either in sulfide minerals or associated with sulfide minerals. And each of these elements that is mined as a sulfide mineral is fundamentally required to make the products that we on average take for granted. If you don't mine sulfides, you cannot have access to those metals. Now, I also have mentioned, and I want to reiterate here, that when we look at metals in the periodic table, and I mentioned this concept called closing the loop, we right now as a global society do truly an horrific, embarrassing job recycling. And certainly we have to increase significantly the efficiency with which we recycle metals. But just to give you back to the example of aluminum, we know that, or we most likely know, we forecast that over the next 60 years, of all of the aluminum we consume, at least 30% will come from freshly mined bauxite. And we know that as we transition, if we continue to transition, and all data point towards a continuation, if we continue our transition towards renewable energy, that can only happen by continuing the mining of sulfides from which we get metals that are fundamentally necessary to build renewable energy resources such as solar panels and wind turbines and battery storage. All of these elements are mined from sulfides. All of them. And there are lots of different types of sulfides. I've mentioned chalcopyrite today, from which we extract copper. There's a sulfide called galena, from which we extract lead. Another sulfide called pyrite, from which we extract iron. So there literally are dozens of sulfide minerals. And I'm not going to go into the details in this class about each of them. But I just want you mentally right now to keep in your head this connection between the stuff that we use, whether it's a smartphone or a Subaru, and what must occur on the other end of the supply chain. And in this case, if we want a Tesla, if we want a solar panel, if we want a wind turbine, we have to accept the need for more sulfides to provide the metals for that renewable energy infrastructure. So the last few slides for today's lecture, or this week's lecture. Mineral deposits are non-renewable. Why? That is a statement of fact. It is not my opinion. It is an objective, factual statement. Mineral deposits are non-renewable. And remember, by mineral deposits, this is what we're talking about. We're talking about volumes of rock that constitute parts of Earth's crust, whether or not it's the rock salt 1,800 feet below the city of Cleveland, whether or not it's the chalcopyrite in the Eagle Mine in the Michigan Upper Peninsula, whether or not it's magnetite and other sulfide minerals in the Bushveld Igneous Complex, whether or not it's aluminum in bauxite in Australia. Mineral deposits are non-renewable. Why? It has to do with time and rates. It's because they form on a geologic timescale, which is much slower than current human consumption. So when we think about how nature forms mineral deposits, the natural recipe, right? Warm water percolating through granite in Australia or in India or Brazil or Guinea, and that warm water leaches potassium and sodium, therefore leaving behind aluminum and enriching the aluminum. When we look at all of these different types of mineral deposits, and the column on the left, that's all these are. So I specifically use the term bauxite today, but here bauxite is a synonym for laterite. So this would be our aluminum bauxite deposits up here. And then if we move down, we've got at the bottom paleoplacer gold deposits. So I talked about placer gold. And what's important to recognize is that each of these different types of mineral deposits has formed at some time in Earth's geologic past. They may be forming today, but all of the mineral deposits that we currently mine and extract, all of those mineral deposits are old. In some cases, they're 100 million years old, or 1 billion years old, or 3 billion years old. And so the x-axis up at the top is age in billions of years, where this line here that I'm moving my cursor over is 3 billion. This line is 2 billion years. And then I'll populate this here with a line for 1 billion years. And then the far right is the Earth's present time. So here's where you and I live today. This is the T. And so we're going from the old Earth on the left to today on the right. And when we look at the time period between 2 and 3 billion years, there are no aluminum bauxite or laterite deposits anywhere on Earth that geologists have found. None. There are a lot of paleoplacer deposits where the word lot is subjective. Okay, let me rephrase that. There have been some paleoplacer gold deposits identified, as well as some of these others that are important. And then if we move forward and say, okay, well, between 2 billion and 1 billion years, we see some other mineral deposits that geologists have found around the world. And the reason that I've put these on this slide, and this is a figure from our book, Chapter 2, there are ways that we can actually determine the age or the time at which deposits form. Meet with me during office hours if you want to chat about those details. And then we move to the present and look at this. For bauxite aluminum deposits, these laterite aluminum deposits, all of the deposits that society currently uses as our source for aluminum are all young. They're all within a few million years of one another, a few million years old of the current time. And one of the things to remember here, you say, well, why is that? Why are there not any really old aluminum deposits? It's because aluminum deposits form at or on Earth's surface. They form in areas where we have warm rainwater hits the surface, percolates through, leaches sodium and potassium, and by mass balance increases the proportion of aluminum. And so what you're looking at here, a snapshot in time over the last 3 billion years for when different mineral deposit types form. So for example, if I train your eye back here to the bottom left, paleoplacer, where paleo means old or ancient, the gold deposits that we mine today as placer deposits, they are all on average older than 2 billion years old. So once we mine all of those deposits and we suck them out of the ground, they're gone. And they're truly gone forever. Now, it doesn't mean the gold is gone. The gold, we have that. And if we increase the efficiency of recycling of gold to 100% and truly close the loop, then that means there is a point in time in the future one can imagine that we don't need to mine paleoplacer gold anymore because there is enough gold in circulation to satisfy human demand. Now, it's hard to imagine today when that period in time in the future will occur, but it is at least hypothetically possible. Contrast that with the top right, bauxite aluminum deposits, where again, remember, bauxite and laterite are synonyms. All of the bauxite that we currently mine and extract aluminum from is all relatively young. So the key is that if humans extract and use natural resources faster than nature makes them, then by definition, they are non-renewable. Nature does not replace them at the same rate that humans use them. And in terms of sustainability, this is where we as a species are challenged to think about how sustainable is our supply of resources based on our current lifestyle in developed countries, what we forecast the lifestyle in developing countries will be in 30, 60, 90 years. We know we have to increase the efficiency of recycling. And we'll talk about that throughout the remainder of the term. And I hope that you come away today really thinking about rates and thinking about how important it is to make sure you always contextualize natural resources in terms of the rate at which they form in nature and the rate at which humans consume them. And for almost every resource we consume today, gold, copper, silver, lanthanum, neodymium, praseodymium, platinum, humans are extracting and consuming those resources faster than nature will replenish them, which means that they are finite, they are exhaustible, and they by definition are non-renewable. And that is the topic for this week, ladies and gentlemen. So thank you all for listening.